Well, welcome everybody to the September 2025 meeting of the Mornington Peninsula Astronomical Society, and I'll move fairly quickly through this. You'll notice in the top middle there that Australia Post has released postage stamps, or will in the next few days release postage stamps of Australian astronomical observatories, and that includes Siding Springs, Melbourne Observatory and Sydney Observatory only. It's a shame they couldn't have included a few more than that, but at least a little bit of presence there. On the top right hand side, if you remember that big earthquake that was in Russia that reached magnitude 8.8, well, by extremely good fortune the day before, the Americans turned on their Guardian network from NASA's JPL, and it monitors tsunamis not by looking at pressure differences in the water like underwater sensors, or looking at sea height, but what it actually looks at is the pressure of the air above the water. So when a tsunami comes by, it squeezes the upper atmosphere, and that affects the radio signals that are coming down from GPS satellites and other satellites. So they're monitoring those satellites and looking for any variation in the radio signals coming down from them. And they were able to detect the tsunami and give a 40-minute warning for it. So they've effectively implemented now it as another tool for detecting tsunamis, quite aside from ones that are based on ocean buoys or seabed ones. Bottom left-hand side, two black holes were merged in January this year, January the 14th, and ANU investigators were involved in that, and they rang like a bell in their gravity waves, and from that they were actually able to work out the areas of the black holes before and after the merger. And you would think if one black hole merges with another black hole that maybe it's not going to be particularly larger, but in this particular case the merger of the two was much bigger than the sum of the two. So it actually expanded after it merged compared to what you saw from the two individual areas, which is really, really strange. Bottom middle one, the Perseverance rover on Mars was in the media for what NASA was saying was the best evidence so far in the search for microbial life. Basically dug up a bit of area of the crater that's been looking at, and it was rich in clay, silt, organic carbon, sulfur, phosphorus and iron. And they found two minerals there called vivianite and gregite, and they're usually associated on Earth with decaying organic matter, or can be produced by microbes. But that's yet to be peer review challenged as to whether or not it can be anything else causing that. And in the bottom right hand side there, NASA has now confirmed that the ISS will be deorbited in 2030, which is not that far away. And in addition to that, they've actually called on commercial industry to replace it, or the equivalent of it, and put permanent crews into orbit instead of the government funding it. So we might yet have big Coca-Cola cans flying in the sky up there with advertising on them yet, as you can just imagine. It would. Okay, so welcome everybody, and I don't think there are any new members here, but the new members since our last announcements were Danielle Nicholas, Kim Hodgetts and family, Georgie Pushner, Diane Morrissey, Sarah Galloway, Gio and Finn Lodi, James Muscat and Jason Sillery, Songlin Mao, Ray Flanagan and David Galloway as well. So we welcome those members if they're watching this online at a later date. Welcome to the Society. I'll quickly go through the events of the past and coming months, and I'll throw over to Chris for Astromofo, assuming there is one. Yep. Then Guido will have Sky for the month, and then we've got a trio of presenters about the Australian Space Summit. And then depending on how we go time-wise, because it is getting on a little bit late, we'll look at what is a photon, the Kessler syndrome, which is to do with space junk and the proliferation of it from collisions in space. and then we'll look at the forgotten computers of the Apollo era, the ones that actually put people on the moon, and look into those. Now, if we don't get through those in time because of the hour, they'll go up on YouTube and you can watch that at a later date. Then we'll close with some footage from the ISS, the International Space Station, set to some music with an African theme. So, recent events. We had Associate Professor Dwayne Hummaker here at the Briars talk about Indigenous astronomy, and that will actually feature in this meeting probably in November. So we'll use that as the video that we show in November of his talk if you actually missed it or you want to see it again. A couple of days later we had a committee meeting which is mainly planning related, and it's coming time to put together the next year's calendar as well before Christmas time, when everyone likes to go and buy little things for people. A couple of days later we had the Monash University's National Indigenous Space Academy interns up here at the Briars. I think it was a bit cloudy, but probably better than past years. No, they didn't have any luck. Oh well, never mind. 1st and 2nd of September we had Toorak College come over 2 nights. They were bussed up here to the Briars as usual, and both very cloudy nights in this particular case, but they all enjoyed themselves, and it was a very high quality of questions that came from them. They'd really put some thought into what they were asking, so a very impressive set of Year 7 girls there. 5th September saw Guido talk at the public night at the Briars, where the cloud cover was a lot kinder. And then we had the astrophotography workshop last Saturday, where we had 29 members turn up, and you see the background photo by John Cleverton there, with Jamie waxing lyrical in the background. Coming soon, it's a little bit leaner. This Saturday we've got the Telescope Learning Day here at the Briars, and there'll also be a buy-sell swap meet if you want to try and get rid of some of your stuff again. It's normally between 4 p.m. and 10 p.m, although of course that's due to weather as well. And you do need to book that online so we know how many are coming. Committee meeting is next week on the 23rd. The next public stargazing night, Trevor will talk on the 3rd of October, and the next cosmology discovery group here on the Saturday is on the 11th of October. Then I believe we're going to have another Indigenous astronomy public stargazing night here at the Briars.
AstroMofo number 26 was a triple challenge. So there was 3 challenges, and the eclipse, an iPhone challenge or a smartphone challenge, and the ongoing Hubble challenge, which we're still doing. So you could either do a combination of getting the eclipse with your phone or getting a Hubble photo with your phone, or whichever way it worked. I'll go through the eclipse photos first, and this was sent in by Greg Walton, which was the lunar eclipse that we just had on the 8th of September, and Greg's done a recreation of our logo, again with a series of images of the moon going from clear through the penumbra, through the umbra, and then I think that's when the last one that he got was. So nice one there by Greg. This challenge was completed by Ali Raymond, who got 2 points. Greg Walton got 3 points, and different points in this one depending on how many of the 3 you managed. So Ali got this eclipse with a smartphone through her Dobsonian, so that's 2 points. Greg Walton managed all 3. Sylvie Grandit got 2 points. Dominic Lucarelli, Fred Prater, Michael Barrow, and myself with the points noted there. So Ali Raymond got her first photo in for AstroMofo. So well done, Ali. And that's her image there of the lunar eclipse with an iPhone through an 8-inch Dobsonian. Okay, Fred Prater sent in some photos as well, and he's got a series of photos there of the moon as it was going through the eclipse, noted in a circle to sort of signify the shadow of the Earth as the moon was going through it, but it's not to scale as is noted, so it's just for artistic purposes, let's say. And as he mentions there, to capture the umbral shadow, the image would include 2.6 moon diameters, so it's not quite to scale there. and also then the photo on the left with his Sony camera too. So a couple of nice photos by Fred, and a couple more here as well. So the lunar eclipse was on the 8th of, oh hang on, I've lost my notes. That's all right, doesn't matter. Okay, now Fred tried to sneak in a double challenge here by light painting with his phone while he took these photos, but I'm not going to allow that. The idea is to use your phone as a camera, not as a torch, but some really beautiful shots there by Fred. So if you don't know what light painting is, it's while you're taking your long exposure, you use a light to paint the foreground with, and that illuminates the foreground while also capturing the stars in the background. So that's what light painting is. So for a few seconds while you're taking your exposure, you just paint the foreground with a torch. So this is actually early in the morning. It would have been pitch dark, but he's managed to light up the trees with his torch to create these shots. So some really, really nice shots there by Fred. And you might have seen this one. And sure enough, here they are. Again, Fred sent this one as well with the his capture of the Orion Nebula on the 8th of September, so the same night as the eclipse. And that image there on the right is the Hubble one. And if you're able to get online, I really recommend going on the NASA website and having a look at that image and getting it up to full resolution, because it really is a pretty spectacular NASA photo, but not to take anything away from Fred's effort as well. Dominic Lucarelli sent in a few photos at a couple of different focal lengths of the eclipse. So this one was at 384 millimeters with a telephoto lens. And then a couple more, 2345, which is a pretty large telescope. I think he's got a Celestron C something, so it would be about that focal length. Next to it, 384 millimeters, and the other small one on the edge there is at 135 millimeter focal length. Sylvie captured a few images as well, so some really nice shots. These are all with the sea star. Is that right, Sylvie? Yep. And yeah, some really terrific shots there, so well done, Sylvie. And Greg's managed a couple with the smartphone through the eyepiece of the telescope, so using eyepiece projection and phone camera on that. Hubble Challenge photos, we've got this one here by Michael Barrow of the Eagle Nebula, Sea Star versus Hubble, so a couple of $100 worth of Chinese telescope versus a few $1 billion of space telescope, and some pretty nice images there for comparison. Greg also captured this one with the Meade, which he sent in. Now I think I'm going to have to start getting picky on these, because I'm going to keep going with the Hubble Challenge, but I'm not going to let you keep sending photos of the same thing in. So if you want to keep sending Hubble photos in, send something you haven't imaged before, because I'll check them. But another nice Eagle Nebula there. We've had a lot of Eagle Nebula photos with this challenge, so but it's all good. Keep sending them. And these ones here by Sylvie as well, Sea Star versus Hubble. And actually, I just should note, Sylvie sent in that Hubble photo, but I've just put it on that screen for comparison, so thanks for sending that, Sylvie. And she sent it to compare these ones, and the one on the left is a mosaic of three images with the Sea Star all the way across to get the whole nebula, so well done. These are by me with my phone on the 127mm refractor down in the observatory, so smartphone on the eyepiece. And there's the jewel box cluster, my version on the left and Hubble version on the right, if you weren't sure. So that's just a single exposure, 15 seconds at 1600 ISO with the smartphone, and just a little bit of a cleanup in Photoshop to get rid of some noise and background, but not a bad effort with a phone. And the other one I got was M17, the Swan Nebula, and again a single exposure with my Samsung, 30 seconds at ISO 1600, and on the right we've got the Hubble photo, so you can see of the Hubble photo, the blue shot how small an area it covers on the of the actual nebula, and it's just really small area up here captured in that Hubble image there. And that was it for this challenge. So we've got our leaderboard up there. I've had to make that pretty small writing. I think I'll put that over 2 pages next time. But Greg's on top with 9 photos, and I don't think Greg's missed the challenge yet, so well done, Greg. And then all the other names of all the other contributors we've had so far this year. So well done, everybody. And the new challenge is comets and asteroids. So we've got 2 comets in the sky at the moment, sitting in the west in the early evening. 2025 R2 Swan and 2025 K1 Atlas are both in the western sky just after sunset. So there's a couple of targets to capture, and they're both, you know, in Virgo, near Mars, and also near Spica, the bright star in Virgo there. Also, the minor planets and asteroids, Ceres is near Saturn, which is a good one to go for, and Vesta is near the head of Scorpio at the moment as well. So a couple you can try and get. The minor planets, the asteroids, Ceres and Vesta, you probably need to get a telescope onto those, but the comets are definitely a wide field capture too. So, and also the Hubble challenge continues, so keep comparing your photos to Hubble images. And just with the asteroid ones, that's just a recent image that I took where I was able to inadvertently, well, wasn't going for it, but that asteroid did turn up in my photo. I haven't had a chance to retake this object yet, but I'm going to retake it and just see that little dot there has moved on. And from what I see on the Stellarium program, it's moved out of that field of view by now, but I didn't get a chance to have another shot at it. Hubble challenge at nasa.gov says where you can get your ideas for your shots and send them in. Thank you very much. Any questions? All good.
We have sky for the month for September and October. And starting with solar system from the top. So we have Earth over here. We can see Mercury is currently hiding behind the sun. Venus relatively close to the sun as well from our point of view. And Mars also now setting a bit earlier in the evening. So if we actually have a look at the outer solar system, you can see Saturn is now pretty much opposite the sun from us. We'll see that in a minute. Neptune basically in the same direction. And Jupiter also pretty close to the sun. So we'll see that in the overview. Let's just watch this while it's going. Okay, so this is over the next month. We can see Mercury reappearing from behind the sun, and Mars will set earlier and earlier, basically. So this is for the 1st of October. So if we look at the sky just before sunset, we can see Mercury very close to the sun there, Mars as well. We'll have sunset around 6:25 on the 1st of October. We have the equinox coming up on the 22nd of this month. Looking at the moon, the new moon on the 22nd, so the day of the equinox actually. Then the next full moon on the 7th of October, and the following new moon on the 21st of October. Okay, lots of planets in the sky here. So this is around 7:15 in the evening. So we have Mercury just about to set there. So it's just coming out of Superior conjunction, and we should get better viewing of Mercury towards the end of October. Mars is now setting around 7 p.m. So that is going to disappear pretty soon as the sun sets a bit later as well. But we have Neptune at opposition on the 23rd of September and Saturn at opposition on the 21st of September, so just in the next few days, which means that they are exactly opposite to the sun from our point of view. So they will be visible all night and closest to the Earth and brightest and so on. So a good opportunity to view those. With Saturn, the interesting thing at the moment is that the rings are closing again. So they were actually at the almost edge on earlier this year and then opened up a bit, and now they're closing up again until the 15th of October, when they will be just at 1 degree, pretty much. And then after that, they will open up again. So we will not, they won't close completely again. But we will have a much better opportunity to view them at that 1 degree angle in October than when we passed through the ring plane earlier this year, when it was far too close to the sun to actually see that. Right, so around the 15th of October should be a really good opportunity to not see the rings, pretty much. Okay, so then if we look at the night sky around 9:30 p.m., 10 p.m., we can see the main stars here. So we have Fomalhaut in the sky and Achernar pretty high in the sky. And the ones I actually wanted to show you, Spica and Mars, have already set, but we'll see that when we look at the new comet a bit later. Looking at the main constellations, well, I guess Orion hasn't quite risen yet at around 10 p.m., but we still have Crux pretty low in the sky now, around 10 p.m., and still have kind of Sagittarius, and where do we have Sagittarius and Scorpius still visible kind of towards the west there. All right. Then
the numbers are next to the minor planets. Is that their size?
The numbers next to the minor planets, I think, are part of the designation. So I think they might be in the order in which they were discovered, because I think Ceres might have been the first one to be discovered. So it's just part of the name, essentially. All right, so we have Uranus rising around 10:30 p.m., Jupiter rising out around 2:30 a.m., but it's back from when it was hiding around the sun. And Venus is a morning object, but it'll stay pretty close to the horizon for the next couple of months, so probably nothing spectacular to view. Sunrise now a lot earlier than last month, around 6 a.m. on the 1st of October. Quick view at the apparent sizes of the planets on the 1st of October. Jupiter is looking pretty big. Saturn is looking pretty big, obviously just past opposition at that point. And the others are not actually, at least Mars, Mercury, Venus are actually not interesting to look at for the next month anyway. All right, comets. We finally have a comet again. So this is Comet C 2025 R2 Swan, the one that Chris just mentioned as part of the MOFO challenge for next month. And this was only discovered a few days ago on the 11th of September, which is quite interesting for such a bright comet. It's already magnitude 6 at the moment, and it was just so close to the sun that it wasn't actually observable before it got that bright. And it was discovered in the SWAN data, and SWAN is an instrument on the SOHO probe, which is basically looking at the sun, looking in the direction of the sun. And so that's where a lot of these comets are discovered now, right? But people basically looking through images from those telescopes and then basically seeing something move in those images, and that's where they are actually discovered. So it was discovered on the 11th of September. It was at its closest point to the sun on the 12th, so it was just around perihelion that it was discovered, and it'll be the closest to Earth on the 19th. When I prepared the slides, I think a lot of this wasn't even known yet. So they're still trying to figure out the exact orbit. What they know is that it's like a long period comet, where its orbital period is much more than 200 years. So it's one of those that might only visit the inner solar system once. It's also not known whether it'll actually survive this trip or whether it's in the process of breaking up at the moment. But yeah, it's currently visible in binoculars around magnitude 6. And I've got a little animation here, so you can see the horizon here at the bottom with the W indicating that's west. You can see Mars and Spica here in the image, and the comet is currently basically between those two. And then if we look at over the next few days, it'll rise a bit higher from the horizon. So hopefully we will get a better view over the next few days. But also, I mean, this is around 8:30 p.m. I think. So there's still an opportunity around 8 p.m., 8:30 p.m. to probably view it. And I thought, because I was looking up different comets and so on, I thought I'd give you a quick overview of what the names actually mean. And so in this case, it's C2025 R2 Swan. And so C means that it's a non-periodic comet. So they call it non-periodic, which just means that the period is longer than 200 years. So it might be, I don't know, 100,000 year period or something like that. 2025 is pretty self-explaining. That's the year of discovery. R is the half month of discovery, right? So the first half of January is A, second half of January is B, first half of February is C, and so on. And so R is the first half of September. And then 2 is just the second comet discovered within the first half of September. So that's what the name means. It's just a systematic way of enumerating all the comets they find every year. And then Swan is just the discoverer, and that could be a person's name if like a real person just looks through a telescope and discovers a comet, but that basically doesn't happen anymore. So most comets now are Atlas or Swan or one of these big kind of telescopes. All right, meteor showers. We have 2 coming up, the Southern Taurids and the Orionids. Southern Taurids between the 10th of September and 20th of November, peaking on the 10th of October. This one will be impacted by the moon around the peak. The Orionids are peaking on the 21st of October, and that's actually around the new moon, so that should be a lot better. And I think that's all. Yep, sources as always, Stellarium, NASA Eyes on the Solar System, and the Astronomy Yearbook. Any questions?
Oh, with the naming of the comets, there was one letter that isn't used. I can't remember if it's I or O. In the half-month letters, there's one that isn't used. That sounds likely. Yeah. Would normally be the second half of September, but it's the first half.
Oh, right. Okay, so there's
I or O isn't used, but I can't remember which one. I think it's O.
Maybe O. So that, I mean, both I and O would make sense that they wouldn't use them. But yeah, okay.
I think it's O.
Yeah. And some of the other letters, I think P is for periodic comets. So all of the short period comets would have a P. And then there's also D. And for example, Shoemaker-Levy 9 is a D comet. And that, I'm not sure if it stands for destroyed, but it basically means that it's gone. So any comet that, like Shoemaker-Levy 9 just crashed into Jupiter, others just disintegrate, and so those get a D designation when they get destroyed. Right, and that's all. Thanks.
In May this year, Dave was invited to go to the Astronomical Society of New South Wales to visit their dark sky site, and I'm his sidekick traveller, so I took my tent, went along as well, and we ended up at the Australian Space Summit, but we actually had a bit of a road trip up there to begin with. Start with the road trip.
Oh, okay. So, is that working? Yeah, okay. So, it's for quite a while, I think we've done 7 or 8 trips up to the South Pacific Star Party. They invited us up there to come up just for some of the regulars to say hello, because the party hasn't run up there now for 3-4 years officially. So they're trying to reconnect with some people that used to be regulars. I'll go into the reasons a bit later on. So that's the road trip up there. It's about an hour north of Bathurst where we're heading to, and it's usually break the drive up because it's just a little bit too far to drive in a day. And we stopped at the Cora Gardens there. Cara. All right, Cara Gardens. Sorry. And then the next day we went on to Bathurst. We found this really good Australian fossil and mineral museum there, and that was actually pretty cool. I liked how they presented it for the kids and stuff. There's a whole section there for Minecraft, which and they'd actually done. There's a few pictures there. I've got a few more I should have put on there, but they'd made a lot of displays very interactive for the kids to get involved. They had a periodic table, and they actually put Lego and stuff in there, and I just thought the way they did it was really cool. It's worth a look if you go in there. How long have we spent there? About 2 hours? More. You can talk about the next slide.
If you're in Bathurst, you have to take your car around Mount Panorama, obviously. So this was me going around Mount Panorama with my... Oh, no, I didn't have my telescope with me. But this was in the wet. Last year was in the dry. So quick whip around.
We actually slowed the footage down.
If you're in the area, you have to do it. Dave's got a caravan, so he has to wait for me at the end. So, and that's it. That's that.
Right, so this is back now at the site of the Astronomical Society of New South Wales, which I've actually spelt wrong on my little note up there, but we all know what's going on. I added a couple of notes because I thought I actually had put nothing in there. I don't even know why I did that.
Sorry, how many others?
There was probably 20-something people on site when we were up there. Came up for that weekend. Weather wasn't flash. We did one good night, which I've got some photos of. Yeah, so it's a bit of a sad story up there. So we found out quite a few of the reasons why they're not running the South Pacific Star Party. There's a whole series of little issues with the council permits and the designation of the use. The amenities up there, they've changed councils or something, and the actual permits for the toilets and so on have been misplaced. What's a few other reasons there? There was about 6 or 7 reasons. Entry and exits on a single road.
Fire hazards, you can touch.
Yeah, that's right. So essentially what it is, any one or two of those things, if that was all, you could probably fix it and then keep running that event. But because there's so many, it's a bit unsure whether it'll actually ever happen again. Yeah, I think we've had 400 or 500 people up there, and it used to be the biggest star party in the Southern Hemisphere for quite a while. And it was on the same weekend as the Texas Star Party, so I had my HF radio up there, and we used to talk to try and make a connection with the Texas Star Party. So then from there we went back to Sydney, and you can talk about it.
We had the most random day in Sydney. Dave told me our first place we were going to was the Freemason Museum, and I don't know any handshakes or passwords. I had no idea I was going to get in there. We were the only people there. I can't believe it. But it was actually really interesting. We were there for ages. We were there for maybe an hour. So we went there. Oh, you got a little Lego guy.
Yeah, they had a Lego temple representation there. So that's actually where the Grand Lodge of Australia is. So if anyone's in the Masonic Lodge, it's an interesting place to visit. Or not.
It was interesting. It was different. It was interesting. Yeah. It filled an hour. And then we went to the War Memorial.
You can't eat it.
You can't take coffee in there, I found out. Yeah, that was actually, we were there for ages as well. That was very interesting. And the reflection pool. And then what's next? Then we walked down to Circular Quay and we went for a tour through the Opera House, which was actually fascinating. Did you know that the interior of the building and the exterior of the building are two completely separate structures, so they can renovate one section without touching the other? That's what I took away from that tour. Yep. And the tiles are not white because then they would be too blinding.
That's right, they'd be too glary.
Yeah, so they're actually like a beigey colour, and they're self-cleaning somehow. From there we... Oh.
What about there? Oh, we went into that's right. So we did the tour inside because I'd never been inside of it. and one of the ladies in our group was a opera singer. So it just happened to be randomly visiting, so she was showing us the acoustics in the building, which were really good actually.
Sounded the same no matter where you were. That's what sound was.
Where are we up to now? Oh, you can see there on the other pictures there, see the internal structure and the outside of the shell, they're not actually connected at all at any point. So that was...
Then we decided to go on a cruise around Sydney Harbour. It was actually started to rain as we were going around, but we saw Kirribilli House, we saw Luna Park, we saw what's the big cruise ship? One of the big Princess.
Yeah, probably Trevor was on it.
Yeah, but it's massive. It can't go under the bridge or anything. We saw, what was that thing in the middle?
At the end of the museum at the end. Sorry, at the end.
I don't.
We saw lots of things.
Yeah. We saw so much that day. So yeah, it was raining while we were on that cruise, but we had to do everything while we were there. We had one day for sightseeing, so we just tried to cram in as much as we could actually cram in.
This was a spare day before the conference started.
Yeah. And then Dave dragged me to the Freemason Museum, so I dragged him to a Stranger Things exhibition. So Dave's never seen Stranger Things, so he still hasn't seen it, but it was not what I was expecting either. It became a little bit of a role-playing thing that we weren't aware was going to happen, and we were separated into groups and we were given superpowers, and it actually ended up being really cool though. There was one room that we went into where it was all 3D. We had to have some 3D glasses, and there were like bats and demogorgons and things like that all flying at us, and Dave whimpered, but something flew at him and he went, ah!
There was real people in there as well.
Yeah. But yeah, it was really good. In the end, you did enjoy it. It was good. He doesn't understand like what we're doing here, but that's...
It looked like an ice cream shop to me, but apparently...
At Scoops Ahoy, we had to go to Scoops Ahoy. So then from there we jumped on... Oh no.
Yeah, that was the ferry on the way back.
Oh yeah, we had then caught the ferry from Luna Park. Stranger Things was at Luna Park, so then we went back on the ferry at night back to Circular Quay, and the Opera House is all lit up because the lights show was on. What's the light show called?
Pollution show.
Yeah, the light pollution show.
Yeah, so it was just City of Lights, about a 2 week showing. I had projections on a lot of the buildings, including the Opera House there. So that was the end of our little trip. And then
we caught up with Guido.
We caught up with Guido at Ozspace, and we got there first day. We all had to get dressed up in business attire, so I don't normally wear a suit, but then Mark and we met him, Mark and Diego there, and yeah, their business attire and our business attire weren't really the same. But anyway, so down below the retirement village had a field day, and they set up a Keep Space for Peace protest out front. I think the youngest person there would have been in their 70s or 80s. They weren't very strong. I think a gust of wind and they would have all fallen over. Not like Melbourne protests, right? So, what are we going to talk about here? So, Professor Alan Duffy was the MC for the whole event. We got to meet old mate there. He came over and said hello to us. He actually saw us out in the room and doing charging across just to introduce himself. I said, ScoMo, there we go. So it was a 2-day event. I should go into it. It was about, what's it, 2 months ago now? This talk's been postponed a few times. 4 months ago, it's true. It was set up over 2 days, and in each part of the day they had 2 streams. They had a blue stream and a red stream with different talks. The first day was definitely more military orientated, so it was more about space defences and there was a lot more military brass there. There was a lot of really not well-dressed people there from the Australian, the US military there. So we're listening to some of their talks. Space Australia Centre was there. So we've got most of these. ScoMo there, he's actually on the board of Space Australia. That's why he was there on that particular day. So there's a rundown of the talks we actually went to. I think you were with us most of the time, Guido, on the talks. So the first days, I got a little bit out of it. A lot of interesting stuff. So years ago, space was mainly accessible mainly only to governments, but now 90% of space launches is actually for the commercial purposes, which has sort of changed the way everything works. And the topic, the focus on the first day was the military, a lot of it, about the denial of service, which was interesting. That's what we're talking about in TeraNet, about jamming satellite signals. A lot of emphasis there on basically they call sovereign technology. So Australia needs to actually develop their own satellites, their own technology, because instead of us having to rely on other countries to manage like our weather satellites and stuff, there's a big push there to actually have controlling Australian satellites, Australian designed, controlled and managed. That was one of the big pushes. And then they spoke quite a bit about hypersonic missile detection systems. Hypersonics obviously are very fast, the rockets there, several times the speed of sound. Ground-based systems that can see horizon to horizon are actually not very good at detecting hypersonics, so it has to be done via space. And the missiles are so fast, there was a lot of talk there about AI and high-speed links. So one thing's to see an incoming threat from a hypersonic weapon, but then able to communicate that and where it's heading to where it's got to go for countermeasures is actually nearly beyond the speed of a human could actually process that data. So a lot of that's pushing out to AI application. So a lot of talk about that. I found it very fascinating, even though it's sort of not what we actually went there for. You can talk about the next slide. Do it. Ruva? Did you see Ruva?
I did see Ruva, yes. So this is the little demo rover that they built, and the project is I'm pretty sure part of the whole Artemis program, where Australia is basically tasked with producing a rover that they can send to the moon and then drive around there. And yeah, so they had the little demo there that was driving around in the sandpit. Was quite nice. I think this was probably one of the very few things that were non-military there and more science-oriented, or let's say non-military or commercial. So there was, I think, the focus of the whole conference was really more on commercial launches or commercial satellites or military or defense applications.
There was amongst the talks there was some stands and quite a few, probably about 20, 30, 25 people, different companies. H-Star was one that's developing launches. A lot of those people are upstarts in Australia trying to get in there in the industry. It's one of my favourite talks, actually. Ted Mercer. Now he was a fantastic speaker. He's so very confident, very American, but he was a general or something in the US military, and now he's in the private sector. So he's actually the CEO of Virginia Spaceport Authority. And one of the things that he spoke about, which was really interesting, is what people don't realise is the spaceport and the rockets are really two separate entities these days. So, in the old days, NASA would build, Cape Canaveral for their own rockets and stuff, and for the launches. But now they've got commercial people paying to use launch facilities. There's no standards, there's no technology setups like, you're building a rocket and then the interface is back to the ground control. There's no standard. So every company that comes in and builds their own rocket have their own requirements on how to fuel it, how to maintain it, and they have to spend months upon months reconfiguring the launch site to suit their rocket. And then if it gets scrubbed or whatever, then they can't do anything else until that rocket launches. So one of the things Ted was driving at was trying to get some sort of standardization between all the different companies all around the world, because some people need to launch to different latitudes. So there might be ESA need to launch something from Australia to get in the right trajectory. But for them to bring over some stuff here and then have to spend 6 months reconfiguring, an Australian launch site at Woomera there or up at up the Cape, just makes it too cost prohibitive to do that. So one of the things they were talking about was trying to get an MOU together on standardising all of that. That's basically requirements to the ground stations. Day 2.
In the morning, people will do the launch.
That's right, that's what's on the screen now. So day 2 we turned up, and it was just as the meeting started at 9 o'clock. It was about 4 minutes to go on the countdown for one of the starships. Was it 2 launches ago? This is the one that got broke up, didn't it, when it got to space? Is that the one that fell down? So it was interesting, though. Everyone, it got off the ground, so half the people were predicting it to be scrubbed, but it didn't. They did launch, but it's just interesting watching everyone in the room there that's actually in the industry, actually glued on the screen about what's happening over there. And the guy sitting in front of us, he was the chief technologist from NASA, sitting like 2 seats in front of us watching this launch, even though it's sort of like the opposition company. But it's just amazing at how that went, and the timing of it was just incredible. Who wants to talk about this one?
I just wanted to explain about the blue stream and the red stream. You'll see we've got headphones on. There were 2 streams running at the same time, but you change the frequency on your headphones depending on which stage you were sitting in front of. That's how there were 2 streams running at the same time, but you weren't interrupted by the other one. So you either had on the blue headphones or you flicked it and they turned into the red headphones.
I didn't watch those.
Okay. I didn't see the first talk there. I did see the second one. That James Palmer there, he's developing the Australian Space Centre up in the Cape York. So he's the guy that's put his house and everything on the line to get a heap of land up there. And I think he just announced on that day they got a heap of extra land given to them. Because he was just saying how hard it is to actually set up one of these launch sites with all the environmental considerations, the birds, the wildlife, the planning, because you can't obviously fly over anyone, and just the amount of effort it's taken to get to the point where they are now. And that's where they launched the Gilmore, was it? Gilmore. That one about 2 months ago, they launched that Gilmore space launch from up there. So, but that was interesting. So that's he's put his life's savings into that. Hopefully, it works out for him. What else were we talking about there? Which one did you go to? Any of them?
I don't remember.
We missed a few. We missed a few talks because there was lots happening on the side. There was a few panels too. You can see there's a picture there. So it wasn't all talks. Some of it was panel talks. Actually, I did catch some of that dual use stuff. They were talking about essentially some satellites sharing technologies like for agriculture and mining and so on, taking trying to, different industries collaborating together on trying to share technologies and so on. So a lot of the talk was about that. Where are we up to now? Autonomous, I did catch that talk, that was good. So what they're talking about there is obviously the time delay. So when you're sending a rover to Mars, you can't give it ground controls because you've got this 7 or 8, 10 minutes delay between what you see and what reaction you get. So they're talking about how AI is actually having to do the task. So it's told you got to do this, and it actually works out how to do it without having to wait for humans to go, oh no, go around that rock to the left and drive it. So there's a lot of talking about that. I'm not too sure what the launch one was on the left.
I think the one on the left was exactly this discussion about interoperability and how you can make launch sites compatible with different types of rockets, and how people like Space Center Australia and Virginia Spaceport can work together to make that happen.
There's more than that, their technology too. There was the fuel, like there's a lot of different fuels they use for different types of rockets. So it's just trying to standardise on all that. There was a big focus on that, and that's what actually made it very interesting for me. Is I'd never ever realised the distinction between the launch facility and the rockets. I always sort of thought they'd develop together, but not these days. All right, Nerida can talk about this. Oh, yeah, you can talk about it.
That was the final. The polar orbit one was the final talk, and so Eric Phillips is one of the astronauts who went on the SpaceX mission that was the first human space flight in a polar orbit, sometime last year, I think, right? And
Frap 2, was it Frap?
I think it was Fram 2, and Fram 1 was one of the, I guess, 19th century or early 20th century polar explorations with like a proper ship, not a spaceship. And he was basically telling a bit about like his life story, because he used to be, or I guess he still is, a polar explorer, and he does like guided tours for probably mostly rich people in very small groups to the poles, and he's done solo trips to the North Pole on skis, and when that was still possible, and also to the South Pole and so on. And apparently on one of those trips he met this billionaire, I think, who got like rich from cryptocurrencies and stuff like that. And then a few weeks later he called him up and said, do you want to come to space with me? And so, because he basically just paid for this trip and invited, I think, 3 or 4 people, I guess the other 3 people from that polar trip to come with him on a trip to space. And that was a really fascinating talk, and he showed some photos he took from orbit, basically revisiting his polar explorations on this polar orbit, and yeah, it was a very nice talk.
Actually, the talk before it was actually good too, there by A.C. Sharma. Can't pronounce it. So he was the chief technologist. Now, he actually broke down a talk really interesting. So he's just left NASA, because apparently they change the chief technologist every 2 or 3 years to keep it fresh and vital. Or Trump got in, one or the other. Anyway. So what he was saying is pretty much every mission that NASA do, they'll list on, probably available on their website, every problem that hasn't been solved yet to make something work. And that list is there. So going to Mars, we have to solve this issue, this issue, this issue. And he broke it right down. And they actually try and get other private people and companies to actually solve each of these independently. So he was just letting us know that that's available. Basically what Australia can do to support some of this stuff, because there's like 30 or 40 line items before they can get a rocket to Mars and return. But the way he broke it down was really, really clear. I looked at the list and thought, yeah, I can't solve any of that. I create more problems than I'd make. And that was pretty much the end of the show. You can talk about after the show, because you stayed on for the extra night.
There was an awards night at the end of the second day, and the National Indigenous Space Academy, that where we just had the students over again a couple of weeks ago, that program was nominated for an award, and that's why I was very happy to join some of my colleagues who were nominated for the award. And so we had a nice dinner, and We didn't win the award, but that was fine. It was still a really fun event to end the whole conference. And that's it.
Ayden's a PhD candidate with the Astrophotonics group at ICRAR, which is the International Centre for Radio Astronomy Research, University of Western Australia. And he serves as Operations Assistant at University of Western Australia's Mardella Observatory. His research focuses on pointing, acquisition and tracking for laser communication systems, culminating in the University of Western Australia-led demonstrations of 100 gigabits per second data rates to drones, aircraft and boats, as well as laser links to low Earth orbit satellites. Currently, Ayden is working on TeraNet 3, the world's first daylight-capable, rapidly deployable optical ground station. This work was recently published in Nature Scientific Reports and won Ayden the Indian Ocean Defence and Security Young Innovator Award. Ayden, by the way, is in Perth, so there's a couple of hours time difference. So the talk tonight, the summary of it is lasers promise to revolutionise the way we communicate with space. By means of their much smaller wavelength, laser communications can provide up to terabytes per second over a single link. However, the extremely narrow divergence of laser signals puts strict requirements on the pointing and tracking systems of a given ground station. In order to increase the versatility of existing systems, which are typically centred around full-scale astronomical observatories, the University of Western Australia is developing TeraNet 3, the world's first rapidly deployable laser communications ground station, featuring a 43 centimetre, or for the older ones here, 17-inch telescope, mounting to a Jeep Gladiator. The system employs a unique three-stage calibration procedure, including the daytime observations of stars, to establish pointing models of 1/1000th of a degree in under 10 minutes from arrival on site during the daytime. In this talk, Ayden will expand on the unique capabilities of TeraNet 3, as well as some rapid tactical deployment scenarios previously inaccessible to laser communication systems. If you have any questions, I'd ask that maybe you hold them off and then we'll walk around the microphone so that Ayden can actually hear them at question time. All right, well, I'll throw over to you, Ayden. Thank you very much.
Maurice, thank you for the introduction. I'll just see if I can share my screen here. So, I mean, I've already been introduced, but yeah, I'll be talking today about TeraNet 3. So that's our rapidly deployable satellite laser comm system that we've developed here at the University of Western Australia. I forgot that I'd given through a little bit of a bio on myself, so I'll recap again, I suppose. But my background is basically physics and maths at a bachelor level at the University of Western Australia, moving on to astronomy and astrophysics at ICRAR, as was described earlier. I basically tangented off from sort of more blue sky fundamental scientific research to more of a experimental sort of aspect. So I've been working a lot on telescopes and telescope systems, whether that be sensors or cameras or software. And that basically has led me into the Astrophotonics group. So what we do is we're using a lot of these existing telescope systems that you'll see later in my talk, just to use those for more unconventional purposes. So that's typically things that the software for the telescopes don't actually provide initially. So we're talking about daytime calibration techniques from the back of a truck, which you'll see later, and also the acquisition of aircraft and drones and boats for these laser comms tests, and that's also the software that I've written there. So at the bottom left, you can see an example of just one of the little user interfaces that we've cooked up. So that basically just governs the control of the telescope, and you can see on the screen there's a little dot that is basically just the tracking test of an airliner that flew past the university. So I'll keep this primarily at a pretty basic level, and then later on I'll jump into some more technical details. This being an astronomical society, I do have a bit of information about like pointing model accuracies and acquisition techniques and things like that hopefully you guys will find interesting. But to start with, I'll just sort of run through space communications in general, just to start at a very broad sort of outreach sort of level. So obviously space communications impact our lives daily, right? And this is the GPS on your phones, weather forecasting, television, even bank transfers use the time synchronization from satellites. Also used for things like Earth observation, for climate change and wildlife research, defense and intelligence. natural disaster responses, and obviously one of the big ones, one of the really interesting ones for the public, space exploration and scientific research. So all of the communications, well, 99.99% of the communications to these satellites are using radio frequencies. Now, this has been the case since Sputnik went up in orbit, right, in the 1950s. So it's great because it passes through clouds and rain. You don't have to worry about weather conditions. And it can also be very easily transmitted in wide beams. So these things typically require the dishes like you see on the right-hand side here. So this can range from receiving a geosynchronous satellite signal, like for your Foxtel dishes, or in the case of deep space missions, you've got your NASA DSN system. So just to sort of contextualize what I mean when I talk about wide beams, here's an example of your sort of GPS transmissions looking back at Earth. Everyone on that side of the planet can receive that signal. So that's one of the really heavily contrasting features between radio and optical, which I'll dive into a little bit later. But radio signals diverge very heavily, and you don't need to be as precise with the tracking systems. So laser communications, on the other hand, use infrared light. So I'm assuming a lot of you, if not all of you, will be familiar with, your fiber optic internet that you have at your home, like your NBN systems. Same principle, but you obviously don't have the ability to plug a fiber optic cable into a satellite. So now you have to basically transmit that via laser over free space. So instead of using a radio dish like you would with your RF communications, now we're talking about basically traditional telescopes with your series of mirrors, right? But why would we bother to do such a thing? So I'll jump into that now. So as technology gets more and more advanced, we're creating more increasing amounts of data on orbit. And there's a fundamental limit to the amount of data that a radio link can carry. So Earth observation, space telescopes, especially JWST, for example, scientific experiments being conducted on the ISS and the upcoming Artemis missions, these all generate huge amounts of data. 2025, we've got better cameras, more expensive sensors that are generating more and more data. And radio is really at a similar level to where it was 20, 30 years ago. We sort of hit the peak, and it's starting to create a bottleneck that we can't really escape from unless we shift away from it. So the reason for that basically is radio sits in the largest part of the electromagnetic spectrum in terms of wavelength. And without getting too in the weeds, that basically it's proportional to its data carrying capacity. So if you're talking about how much data you can squeeze into a link, per unit time, the smaller the wavelength, the better. If you want to have like a very playground analogy here, say the message you want to communicate takes 10 wavelengths. If you look at this little animation here, I'm not sure if it'll be coming through very well, but you can basically see that's only a 5 times difference, and you can already intuitively imagine, right, shrinking the wavelength is going to get my message across a lot faster. And then if we start to talk about the data rate comparisons between radio and lasers, we've gone from kilobytes to megabytes per second up to gigabytes to terabytes. So this slide I originally had for a school talk. So I don't know if any of you would be interested in the size of downloading Call of Duty, but the time to download this with a 1 megabyte radio link is about 65 hours. The world record for free space optical transmission at this point, held by DLR, is about 13 terabytes per second. So this would take 0.018 seconds by comparison. So that's obviously the world record, but just a bit of context in terms of like the heavy difference in terms of data carrying capacity between the two techniques here. So what have I got? That would also be 6.8 million 4K simultaneous Netflix streams. So it's a lot of data. So I'll explain now a little bit about what I do and what my research team does here in Western Australia. So as I alluded to earlier, we've spent several years developing laser communications technology. So that culminated, as you would have heard earlier, in demonstrations to drones, helicopters and fixed wing aircraft, boats, and more recently, we've finally moved on to satellites. So the system that I'll be talking about in a second, TeraNet 3, is part of this $6.5 million ASA grant to develop a 3-node optical ground station network. So that's our TeraNet optical ground station system. So we've got TeraNet 1 at the University of Western Australia. So that's a 0.7 meter telescope on the roof of the physics department. We have TeraNet 2 up in Mingenew. Again, it's a 0.7 telescope, but it's in the Geoscience Australia Space Precinct. And then TeraNet 3, which is mobile. So there's a pin there, excuse me. There's a pin there for ESA's new Norcia site, which we're doing some commissioning at. But generally speaking, it's mobile. So it can be anywhere in Western Australia or Australia. So because lasers can't pass through cloud the same way that radio communications can, as I mentioned earlier. The ability to move to places where there are clear skies is obviously quite advantageous. So you can maintain communications with your satellites without having to basically create a spatially distinct series of ground station nodes that would obviously cost you several $1 million to set up each individual node. The method, or the idea behind TeraNet 3 is to basically achieve that level of versatility while only having to produce one system. And also with that comes a bunch of, as you can imagine, defense applications for sort of your rapid tactical deployment. So TeraNet 3, which you can see on the right-hand side here, that has a PlaneWave L500 and CDK17 mounted onto the back of a Jeep Gladiator. So these are more up-to-date pictures than you would have seen on my opening slide. So we now have a mechanized canopy on the back and also a mechanized lifting mechanism, so that theoretically this can be controlled by one operator and then deployed and not have to do any sort of manual labor or heavy lifting or calibrations. That should all be in place from when it was properly calibrated last time. So it's capable of being basically deployed anywhere and ready for satellite communications within 15 minutes. And one of the really important things to note here is that includes during the day. So we're not the first attempt to make a mobile optical ground station, but we are the first to really hammer down on daytime deployment capability. If you're looking for sort of rapid deployments to plug the gaps in a network where, you know, adverse weather conditions may have blocked out some of your other nodes, waiting until nighttime isn't always necessarily, you know, what word do I want to use here? Yeah, isn't always basically enough. So you need to be able to deploy quickly, set up, and have that operational. And if that means it's during the day, then it has to be during the day, basically. So this is something that we've only done and no one else in the world has done at this point. So one of the really important things about laser communications is you have to hit a satellite with a laser pointer. So that's basically, as described earlier, my job. So it's basically to interpret all these sensors, well, first to procure and mount all these sensors, integrate them into the software, to design the software, and then have all of those things sort of play together nicely and culminate in hitting a satellite that can be, as you can see on the right-hand side there, rather small when traveling at 60,000 k's an hour. So this is the very outreachy version of what I'm about to describe. So in order to do that, we're basically operating in near infrared so that we can cut through some of that Rayleigh scattering. And we can see about on the order of 100 to 200 stars in the middle of the day. So as I'm sure some of you would be aware with your pointing model calibrations, you can use their positions to figure out exactly where your telescope is oriented, and then you can use that for your satellite acquisition. So we're talking about to within about an arc second for our closed loop tracking. So I'll just pause for 1 second, get my breath back. So this is the additional content that I have jammed in to my otherwise pretty tame outreach talk. So hopefully some of you in the audience, I can't obviously see, but you'd obviously be familiar with the concept of plate solving for your pointing model calibrations. Now, something like that won't work in the day, at least in our sort of scenario. So in order to get that telescope calibrated to the point where we then can do, you know, precise acquisition of satellites, we've developed this 3-stage method. So that starts with sort of your inertial measurement unit. And to get something plus or minus a degree, you're looking at a relatively cheap, you know, non-ITAR military grade system. We then operate on a 5-degree wide field of view camera. You can see, I'm pointing at the screen, sorry. You can see piggyback onto the top of the telescope there. And then once that sort of has created a model of sufficient accuracy, we can then go hunting for stars through the main aperture, which is obviously quite narrow for a 17-inch telescope. So just to contextualize a little bit why we're operating in near infrared, this is your emission curve for Rayleigh scattering. So you see that black line there with the arrow, we're basically chopping off everything to the left of that line. So we're getting rid of a lot of the emission that you're seeing in the sky, making it more transparent in the spectral response range of the camera post filter introduction. And then obviously, if you look at your first order approximation for stellar emissions, we are then seeing, you know, a lot of your red stars, Not so much your blue stars. Stars like Sirius are no longer the brightest stars in the sky once you apply a filter like this and you start operating in near infrared. But there are still plenty of stars where their emissions are quite hefty. And by going for them, we can reduce the amount of blue we're seeing in the sky and basically pluck a lot of these stars out with relative ease. So I'll explain a little bit now about the two camera systems. So I won't bore you all with the technical details about the make and the model. What you can see in the image here is basically our, what you can see here is our computer vision software. So that little green circle basically indicates that the search algorithm that's running over the image that's come out of that camera has identified a star. So we've got basically the introduction of our IMU, which gives us our coarse sort of orientation to within a few degrees. We then basically go hunting for the brightest few stars with this wide field camera. So as I said, we're operating in the I band now. We're not looking for stars that are bright to the naked eye. We're looking for stars that are specifically bright in infrared. So we'll go and acquire a few of those, co-align them into the main aperture of the camera. And then on the right-hand side here, you can see that's basically a shortwave infrared camera operating in the main aperture. So the advantage of using that instead of just a regular camera with a long pass filter on it is that has the ability to actually image the laser signals incoming themselves, which is brilliant because if we're looking at doing communications with satellites as small as the ones that I showed you before, that will obviously be invisible. You're not going to have any hope of seeing those even if they are sunlit. We can actually closed loop track on the signal itself. So you'll see the downlink signal in your camera, and you can use that to precisely align and maintain alignment during the communications testing. So here's a bit of an explanation in terms of how the pointing model converges over time. I know it was mentioned earlier that we can sort of go on sky within 10 minutes. So this is what you're looking like in terms of convergence. It's obviously a bit hand wavy in terms of what you would consider a sufficient accuracy to then go hunting after stars, given your errors and satellite ephemeris and things like that. But we can get down to about 3.5 arc seconds after 9 minutes. And generally speaking, that's more than sufficient to then go and identify your satellites and then closed loop track. In closed loop tracking, once we've actually received the signal, we're looking at about 1 arc second RMS, or median-ish in terms of error. So I'll just show a little video here now. Hopefully this works. Yep. So this is basically the procedure in terms of arriving on site. You can see the canopy opens there. Telescope basically has that mechanism to put it up into position, and then the mount drivers can power on and you can go about your business in terms of actually doing your calibration technique. So one of the other advantages, there we go, in terms of using the plane wave system that we've actually got on the Jeep, is a lot of our demonstrations previously that I mentioned that have been to aircraft and to boats. All of these have actually relied on a plane wave L350. And because of the fact that the software is identical between the two of them, the Jeep system, TeraNet 3, now immediately inherits all of these capabilities. So we also have a system that can do this daylight acquisition, do its calibration, go hunting after satellites for satellite communications, but at the same time, it's now capable of doing point-to-point communications to land targets, to maritime targets, or to aircraft as well. So this is a summary that I displayed at a defense conference. I might be a little bit out of context here, but this is the sort of summary. So if I was to sales pitch it to you, basically, so as TeraNet 3 can be rapidly deployed to contested or GPS denied environments, I can allude to that in question time if anyone's interested. Parked on the side of a hill in broad daylight and be ready for SATCOM in 10 minutes. So in terms of, as I said earlier, the alternative, which is to assure constant communications with your on-orbit assets and building several ground station nodes, it's obviously a cost-effective alternative in a more research or commercial sense. But basically, given that there's only so many users who are necessarily interested in the ability to rapidly deploy a system, pull it back down and then disappear, we're getting a lot of interest at a more defense and national security level, because there is no other system that necessarily fits this application. And we are seeing the rise of optical communications, not only in a commercial setting, but also in a defense and national security setting as well. And one of the advantages of having such a large telescope on the back and having it calibrated is that we can now also use that telescope for sort of space situational awareness observations. So you have basically a telescope that's rapidly deployed and calibrated. You don't necessarily need to use it for satellite communications if you're not interested in that. Just the ability to perform that calibration and deploy it now gives you that telescope as an asset to do whatever it is you want to do with it. So I'll leave this up here. I haven't necessarily gone too much in the weeds, I don't think. For those of you who are interested in the more nitty-gritty details, if you do scan that QR code, it'll direct you to a little link tree that has an academic poster that I put out a few months ago, but more crucially, it has the actual Nature Scientific Reports paper. Now that goes into quite a lot of detail in terms of, I would say, like the automation and the software and the imaging techniques to actually get the star calibration working. One more thing, for any of you who are going to IAC in Sydney, we have actually shipped the Jeep over. So if you attend, I'll be there. The Jeep will actually be there in the exhibition hall. So feel free to come up and talk to me, and I can elaborate on anything that we don't get covered tonight. So thank you.
Okay, thanks, Ayden. We'll throw over to any questions from the audience.
Yeah, thanks, Ayden. So how do you propose to get the data from the mobile Jeep, TeraNet 3, to a situation? So if you're on the hilltop, well away from infrastructure, you're still going to get that data from the Jeep to somewhere that needs that data.
Yep. Well, I mean, that's more of a user problem, but I understand what you're saying. So there's obviously the option of having, I don't know, predetermined deployment sites where you would have some sort of fiber plug-in at the deployment site. But one of the really important things in terms of that on-orbit bottleneck is that as long as that data is on the satellite and it's not coming down to the ground, that satellite's basically full. And it's diminished its ability to actually get more data. So even if you do get the data off the satellite, you have to then drive for several hours to go and actually reintroduce it to like your ground-based, Australia-wide system, global system. If it's off the satellite's free again, basically, and that's in a lot of cases the important part.
Well, one question I have, Ayden, is what is the actual range of this from the ground? Are we talking about very low Earth orbit satellites, or geostationary, or potentially even satellites around the moon?
It's a bit of a tricky question because all of this sort of depends on link budgets. So basically the transmission power of the satellite, and then you do all the fancy maths and figure out, the area of your receiving mirror size minus your secondary obscuration and all that fancy stuff. But typically we're talking low Earth orbit. All the satellites that have been, all the ground stations that have been utilized for sort of your deep space communications typically have telescope sizes of a meter or larger. We've aimed for 0.7 to be a happy medium. So we're not basically having to invest too much money in obviously exponentially increasing infrastructure costs to get large telescopes. But if you had a sufficiently powerful satellite transmission, theoretically you could be looking at GEO, but this was really aimed at LEO, and LEO has the larger constraints in terms of downlinks as well. Probably mention, because obviously LEO satellites only have a footprint where they can see, say, 1,000 kilometers around. Getting the data down and having a specific ground station in a specific spot becomes more important than your GEOs that can necessarily see half the planet. So if something's covered over, they can just downlink to the other one, right? So this was really to plug the hole in the LEO downlink capability.
I'm not sure if this is a dumb question or not, but do new satellites have to have something fitted that will read from a laser instead of radio so that they can talk to each other?
Yeah. No. Yes, definitely. I mean, we're seeing lots and lots of satellite constellations these days go up with inter-satellite laser communications links. Like all your Starlink satellites right now actually communicate to one another using lasers. That's a bit easier than it is going from ground to space because you don't have the atmosphere to contest with, you don't have adverse weather conditions, all those things. Ground to space laser communications isn't as popular yet. In some senses, it's still a bit of an academic pursuit. We are seeing defense agencies in America start to use it. Companies start to use it. But it's really something that needs to be adopted before I think companies are going to be confident enough to, like you said, actually put constraints on their satellites that requires a laser communications downlink to work. So to answer your question, yes, it needs to be specifically designed, and people need to be confident enough to actually move forward with its introduction.
I had a question about the pointing accuracy. If you could compare that with, let's say, for example, the Deep Space Network tracking Voyager very far out in space. Obviously, that's like a massive, like 70-meter dish or something, having to also point very accurately at something that's very far away. And now you're pointing at something extremely small with a much smaller telescope. So can you maybe compare the accuracy that's needed for those two things?
I would love to if I knew the accuracy of the Voyager ground stations off the top of my head. I think I can compare it to a typical sort of laser comms observatory. So like for our fixed nodes, our 0.7 meters, which obviously have the luxury of being in a dome that doesn't move. So it's a regular astronomical observatory. We're looking at on the order of about an arc second for our pointing model accuracy. So when I say that, I mean open loop. You basically plug in the RA index of a star, and you're basically just doing that over and over to see, on average, how far off are you actually pointing to where you're supposed to be pointing. So that's how I derive, if I flick back a little bit, that's how you basically get this. So that was just the jig going after a bunch of stars for several hours. It took a very long time to get all those data points. But 3.5 arc seconds is some of the other mobile action. I don't want to get this wrong if we're recording this, but basically it seems like we're actually operating at a higher level of accuracy than existing ground stations. Again, without giving you a boring answer and getting into the weeds, the requirement for accuracy then comes into uplink beacons and more communications protocol specific things. But if anything, the largest source of accuracy, once you're calibrated to this point, is actually going to be your ability to sort of convert the satellite's orbital information into positions accurately. Your satellite TLEs will actually introduce more error than the pointing calibration will at this level. So.
Hi, Ayden. I've got a question regarding the Jeep that you use. I won't ask how often it breaks down. What I will ask is, what sort of challenges did you have with respect to stabilising it enough so that it is able to be stable enough for you to point with the accuracy that you need to point to? Did you have to modify it, or do you need to put stands down when it's parked, or how do you cope with that?
Yep. So basically, the work that I did, and you'll see that represented in the very first slide that I had, where the Jeep basically looked like it was straight out of the dealership. It started with no modifications at all. The idea being that a lot of laser communications payloads on ground segments tend to have what's called a fast steering mirror. So that's for your tip tilt. And they operate at several hundred hertz to a kilohertz, and that's to correct for your really rapid atmospheric fluctuations. So you see a star twinkling, and that's just your first order modes to start correcting for that. So your more complicated adaptive optics systems will delve deeper, but to start with, you basically correct for it with just that spatial flickering. The brilliant part about that is now we have a system that's accurately targeting at several hundred frames a second, and it's got basically no inertia because it's a tiny mirror, and we don't have to stabilize the Jeep anymore. So basically the Jeep can rock around, and it's obviously a very low frequency, large scale rocking. And the main thing about that basically is the fact that the Gladiator is a giant wind sail from its side profile. So if you park this thing anywhere near a beach or the river, you'll just get flogged and the suspension will rock like that. That will throw your pointing calibration out a little bit. There's some tricks around that I won't go into, but the idea was to avoid having to have something like, like pneumatic legs or any sort of specific site requirements like that, because a lot of the other systems that you see globally have that, and the idea was we wanted to keep this as sort of flexible and as low cost as possible. So by having all the sort of movements corrected by a mirror, struck us as a better solution than introducing any more complicated hardware.
Does that mean you could actually do this while driving?
So the mirror has an actuation range, like an angular actuation range. First of all, I wouldn't feel comfortable driving this thing with the plane wave telescope on the back, because when you put too much force on these mounts, they basically disengage. So if you go over a bump and the outdrive disengages, or even the as-drive, right, then you go around a corner, it just swings and smacks into someone. But yeah, if you could get a tip-tilt mirror with an on-sky range large enough to compensate for, say, going over a bump or something like that, then in theory, yes. There have been very, very expensive, US defense prime-led demonstrations from aircraft before, and they're obviously moving, but they don't have to go over bumps or turbulence, but not necessarily the same sort of thing. So it's possible, definitely, with more expensive and complicated hardware.
You noted, Ayden, that defence industries were obviously very interested in it. I think one of the things defence is increasingly relying on satellites for targeting and communications across the globe. At the moment they communicate via radio, which is obviously easy to interfere with, which is focus of other militaries is countermeasures. How vulnerable do you see a laser being to countermeasures? It would seem to me to be a little bit more invulnerable.
Yeah, no, definitely. I mean, that's one of the big sales pitches when we're talking to either defence personnel or defence industry primers. We're trying to, communicate this across to them. Obviously, when you're transmitting radio, like you said, people can eavesdrop. They can jam your communications. They can use your communications to try and triangulate where it's coming from. One of the things about laser comms is you basically can't see it unless you're inside the footprint of it. So it's low probability of detection, low probability of intercept. So in terms of being covert, it's brilliant. We're talking to some people from the Navy about particular scenarios where they're actually going to go radio silent and use, I forgot the word for it is, but basically the lamps with the shutters on them to very slowly communicate across to each other some messages, because they can't use radio. Whereas something like this could obviously be employed in a point-to-point sense, and suddenly you've got limitless data and it can't be detected and you're still radio silent. Yeah. So in terms of jamming, you basically can't jam laser communications because of how specific you have to be in terms of actually pointing at each other. You would have to be within the two. And if we're talking about satellite communications, for instance, you would basically have to have an aircraft that has somehow magically figured out exactly the spatial position or the angular position from the point of view of the observer and replicated that just to get exactly within the footprint of a laser transmission, which would probably be about that big, at a couple of 100 meters or kilometers. So in answer to your question, it's a lot more secure, but it's a lot more vulnerable to a little bit of apprehension in terms of switching for arguably more reliable radio systems.
And what's the power of the laser in the sense of if you get a seagull fly over at the wrong height and the wrong position?
So again, yeah, I'm sorry I couldn't be more specific, but all of these things are different case to case, right? We're only talking about a couple of watts, okay. But depending on beam divergences and things like that, a couple of watts still can be not eye safe for meters to hundreds of meters. TeraNet 2, its location is actually within a no-fly zone for satellite laser ranging. We're co-located with Geoscience Australia's Yarragadee satellite laser ranging facility, which is brilliant because then we don't have to worry about aircraft. But for TeraNet 3 and TeraNet 1, so the one that I spoke about that was on the roof of physics, and obviously this mobile system, that aircraft is obviously a huge consideration because you can't go shooting lasers at aircraft. But for the most part, it would basically be a distraction and still illegal as far as CAS is concerned, but you would have to be relatively close for it to cause any damage.
What sort of beam width would you have on a laser by the time it got out to a satellite?
So, I mean, I can talk the inverse, just because I haven't got the maths in my head about our uplink signals. But when we're talking about, so DLR has this flying laptop satellite, which we've done some communications tests with. So it's a little CubeSat, but it's got an optical downlink payload on it. It's been up for a few years. It's operated by, I believe, the University of Stuttgart now. But the actual footprint of the laser itself, by the time it gets down to the ground, is a couple of 100 meters. Which sounds quite reasonable when you're looking at it from a ground perspective. When you're looking up and you consider the fact that the satellite's obviously doing 40 to 60,000 k's an hour, that gets small very, very quickly. It's probably a good time to mention as well, when I mentioned earlier about the inaccuracies in your satellite orbital information, clock synchronization is also a really important factor as well, because as I just mentioned, if you're going that quickly and your clock's out by half a second, and you're going 60,000 k's an hour, that's a lot of distance that you've now, miscued your uplink signal by.
So what were the main differences between TeraNet 1, 2 and 3? Because I noticed you had 3 on the map that you showed.
Yep, sure. So 1 and 2 are basically your traditional observatory-based ground stations. So 1 was basically, if anyone's heard of the Spirit Network, it's basically a astronomy outreach program out of ICRAR. It used to house a 1 meter telescope used to house a 70 centimeter telescope, I believe, in that dome just for regular astronomical imaging. The one up at Minganusa TeraNet 2 is the same sort of story. It's a planewave RC700. And again, it's basically just an observatory. TN3 is definitely the odd one out in the sense that it is completely mobile. So that's basically our experimental trying to push the versatility boundary. The other two are more traditional, reliable, will function as an actual ground station network nodes, whereas, this is our sort of experimental academic exercise.
So do you see a foreseeable future whereby it could be put on a large drone and taken above cloud level?
Potentially. I mean, again, it all depends on link budgets, because as I mentioned, depending on the transmit power of the satellite, that will determine the size of mirror you can get away with. So if it's a stronger laser, you can have a smaller mirror and still get a sufficient level of light back into your system. So if you either had a drone big enough to carry a mirror of the sufficient size, or a satellite powerful enough to mean that you can get away with a really small mirror, then technically, as I said before, there have been some full-scale aircraft testing that's been done. The Americans have done some, I believe, in the Netherlands. I think TNO, the company, is also doing some aircraft testing from satellites as well, which is kind of exactly what you're mentioning as well, because you can be up at 40,000 feet. I don't see why drones couldn't get in on that party either. It sounds like a fun project.
Any other questions? Okay, I think that's all. Thank you very much, Ayden, for speaking with us and putting up with the vagaries of Zoom.
No worries. No, thank you for having me. As I mentioned, if everyone wants to scan that, that is where all the other information will be, if anyone wants boring technical details that I've tried to spare you from as best I could today.
Maybe before you go, not TeraNet related, but can you tell us a little bit about your Mardella Observatory?
Oh, sure. Yeah, okay. So as I mentioned earlier, ICRAR has a thing called the Spirit program. So basically, it's an online, it's a, I want to find a better way to phrase this. Basically, there's an outreach program where ICRAR goes to schools and basically tries to teach astronomy. And what the Spirit program is it's basically an online portal where you can submit observations and have the robotic observatory go and take those observations of the RA and DAC you wanted, the particular bands, exposure time, and then take the images. And when they're completed, they'll get emailed to you, and then you can do your processing, whether that just be for astrophotography or some of the undergrad or postgraduate students have projects at UWA where you're doing photometry, taking a BTEC V measurements and color magnitudes and things like that. But basically, I am an operations assistant there. So that basically just means I have to monitor, I think we have 6 telescopes at this point. One of them's a 1 meter. It's a big hefty telescope, and just basically make sure that all the little bits and pieces, a lot of the network stuff and the camera sensors and the power systems and the online portals and everything all play nicely, because it's basically a system that's constructed of bits from 150 different. They need someone to keep an eye on them at all times, basically. So that's my job, to make sure things don't catch fire. But if anyone wants to Google the Spirit program, maybe Google like ICRAR Spirit, you'll get more information there.
Is that only available to schools and educational institutions, or could potentially astronomical societies participate in it as well?
Oh no, definitely. No, I mean, there's certainly times where the telescopes are sitting there dormant. So if anyone, yourself, I don't know if you want to, there's a contact email on the website, and I'm sure we'd be happy to facilitate anyone wanting to take observations. Because as I said, we've got a 1 meter telescope, and it pains me to sit there on several nights and see it not doing anything. So I'm sure if there's anyone eager, we'd be able to sort something out for you.
Oh, thank you very much from Melbourne. Have a good evening.
No worries. Thanks, guys.
Okay.
A photon is supposed to be a particle of light, but this is not a photon, and neither is a point particle like this. That's because I think the term particle of light is extremely misleading, because at least to my mind, and I think for most people, the idea of a particle is that it's small, like it's confined to a certain area, and it moves along kind of like this. But as I'll explain in this video, photons are actually huge. They're infinitely large, spread out over a huge amount of space, and they move along like this. But wait, is a photon just a wave then? What about the particleness? Well, I'll explain in this video how a wave like this can still have a discrete and particle-like property about it, which is what makes it a photon. But I'll also explain how if you measure a photon, you end up getting a discrete particle like this somewhere along here, which you may have seen in famous photos like this, where single photon dots make up the double slit pattern. This is not a contradiction in quantum mechanics. It is possible for something to be very spread out before it's measured, and then when it is measured, it collapses to a single spot. And we'll explain in this video how that happens, like mechanistically, what goes on to force the photon into a small spot when it's measured. Okay, so I wanted to explain this all to you using an experiment called the photoelectric effect, which is really important in quantum mechanics because it was the first experiment that convinced people that photons exist, that there are particles of light. The original version of the experiment is quite complicated, so I was going to show you an at-home version, which was based on a few other YouTube videos that I'd seen with, but I wanted to do it slightly differently. I was going to do it with calcium and visible light, so you could really see what was going on. At least that was the plan, but it just didn't work, and I don't know why.
No.
I don't get it. So instead, what I'm going to do is I'll link to some other people's videos where they do manage to get it to work at home, and then I'll explain what I should have seen when I did the experiment. This is my diagram of the experiment. I know it looks like a weird game of hangman, but this is supposed to be the calcium metal, and here in the cup is supposed to be these bits of foil. And I started off the experiment by rubbing my hair with a plastic bottle. The point of this is that when the plastic bottle rubs against my hair, it steals some of the electrons from my hair. And then when I touch that plastic bottle against the calcium, it donates some of those extra electrons to the calcium, making the calcium net negative. But because the calcium is in electrical contact with the foil, that should make the two bits of foil move apart from each other because they're both negative. At least that was what was supposed to happen. No, nothing. Nothing. So much for that. That was the easy part of the experiment. That was just the setup, right? Like, I have no idea why that didn't work. I think from now on, I'm just gonna stick with theory. But anyway, let's assume that that did happen. Now, the important part of the experiment is what happens when we shine some light on the calcium. Light has energy in it, and there are electrons that are trapped inside of this calcium because they lack energy. They don't have enough energy to escape. So in theory, by shining a light on these electrons, you might be able to give them enough energy to escape. That's what the whole photoelectric experiment is about. Whether this light is going to give enough energy to these electrons to make them escape. If it does make a bunch of electrons fly away, then we'll be able to tell, because now the negative charges will spread out again and they'll be basically neutralized. And so these two bits of foil can now go back to being together. So that's what we're looking for. We're looking to see, does this light let electrons escape? All right, so first up, we'll put some red light on. And red light has quite long wavelength. But in classical electromagnetism, it doesn't matter what the wavelength of the light is, it only matters how strong it is. So we first shine this red light weakly, and we see that nothing happens. The electrons stay where they are, and the foil is still separated. And so then you might think, well, all we have to do is add more energy. And in classical electromagnetism, more energy just means a bigger amplitude. And so we turn up the amplitude of the light, making it brighter, which means that there's much more energy in there. And so this should be enough energy to release the electron. But we find that no matter how bright you make that red light, you will not be able to release these electrons, and the foil will stay as it is. It's the same story when you instead use yellow light. You can shine the yellow light as hard as you want, but it's not going to release any of the electrons. But things change when you instead shine some green light. Now what happens is that the electrons do get freed, and these bits of foil come together. And this will also happen when we use blue light, which has even shorter wavelength. So what we found is that the intensity of the light just doesn't really matter for whether the electrons will get released or not. But the wavelength does matter. As long as the wavelength is lower than some threshold wavelength, then the light will release electrons. In our case, for calcium, it turned out that calcium requires green light or light with shorter wavelength than green. And that's why I was really excited to try and use calcium for this experiment, because it's kind of cool to see it in the visible spectrum where, like, you know, red light doesn't work, but blue light does work. Usually for the kind of metals that are used in a lot of experiments on YouTube, like the only light that does work is like ultraviolet and above. And so it's a little bit less exciting to see that, I feel like. But I mean, how exciting is it to see this like diagram of the experiment? Anyway, the point is that this result was very, very surprising when people first did it, because this is the opposite of what you would expect from classical electromagnetism. Here's what that theory would have said. Light has energy in it, and the brighter the light, the more energy it's got. And the way that energy manifests for a wave is in its amplitude. The bigger it is, the more energy it has. In fact, the amount of energy in light is proportional to the amplitude squared. So for the energy of the light, it doesn't matter at all what the wavelength is, just how big the peaks are. The wavelength just determines the color, but the amplitude is the energy. The thing light wants to do with all of that energy is donate it to a charged particle, like this electron here. When the electron is all alone, it can receive any amount of light. The more it gets, the faster it flies off. But it's a little bit more complicated when the electron is bound up in a metal. The reason the electron is trapped in the metal in the first place is because it doesn't have enough energy to fly away. For each metal, there's a fixed amount of energy that the electron would need to break free. When light shines on it, that's the electron's opportunity for escape. The electron doesn't mind what color it is. As long as there's enough energy in the light to break it out, the electron can escape. The extra energy then might just go into how fast it flies off. Only this story is what you would expect from classical electromagnetic theory, and it turns out not to be right. So for the classical wave theory of light, the intensity, which is related to the amplitude of the light, is the only thing that should matter. But the wavelength, which is related to the color, should be completely irrelevant. But that's not what we found at all. It took Einstein coming along in 1905 to come up with an explanation for this experiment, and his explanation was a bit of a compromise. So he said that waves like this still have energy that is related to their amplitude. However, it's not possible to make the wave weaker and weaker in a continuous manner like this. Instead, waves must have a minimum amount of energy. A wave with this minimum amount of energy is called a photon. But there's another rule to this. If you wanted to add energy to this light, you can't just add any amount that you want. Instead, you have to add another photon's worth of energy, which is the same amount of energy. This new wave has a bigger amplitude, and it's called a 2-photon state. So to generalize, any wave of a single color of light must be made out of a whole number of photons. Which is all very interesting, but what has this all got to do with the photoelectric effect and color and all of that? Well, the size of this minimum amount of energy, in other words, the energy of a photon, depends on the color. So if I have some light that has double the wavelength, then it has half as much energy inside of each of its photons. So here's a question for you. If I had these two bits of light then, and both of them actually had the same intensity, then what would that tell you about the number of photons inside? Well, if this light has, let's say, 2 photons worth of energy in it, and this light has the same amplitude as this one, it must have the same energy. But because each of the photons have half as much energy in this case, there must be twice as many photons to make up for the difference. So in total, the energy is related to the amplitude, but the photons are just about how you're allowed to chop up that energy. The really crucial thing for the photoelectric effect is that the longer the wavelength, the smaller the amount of energy per photon. Now, the actual equation doesn't really matter too much, but just knowing this will be enough to understand the photoelectric effect. When light interacts with an electron, instead of giving that electron all of the energy, it gives the electron just 1 photon's worth. We'll get back to why in a moment because that is super important, but for now let's just go along with it. So let's say we have a color of light that has really big photons. And so if that 1 photon has enough energy to free the electron will take that freedom plus any surplus energy will just go into its kinetic energy. On the other hand, we might have another color of light shining with a lot less energy per photon. Now the electron won't get enough energy to escape from 1 photon. So it doesn't take any energy at all. Even though many photons may be raining down on it, none of them are good enough. So it's the fact that energy is broken up into chunks like this, and that electrons can only take 1 chunk at a time, that explains the photoelectric effect. But what does this tell us about photons? Like, what are photons? Well, we can now see what's sort of discrete and particle-like about these photons. The amount of energy is discretized, and so we can talk about like a number of photons inside of the light, which feels very particle-like. But on the other hand, they're not particle-like in that it's nothing to do with how spread out they are in space. Now, I know that doesn't sound very satisfying because I think the word particle very much evokes something that is confined in space, which is why I think this picture of a photon has become very popular. Honestly, I used to think that photons look like this. I mean, it's so tempting, right? It's still a wave, it's still wavy, but it's confined to a certain space. It just seems like this is what a photon should be. It's so tempting to think of something like this as a photon, rather than an infinite wave like this. I mean, this moving along like that looks way more particle-like than this moving like this. And plus, you've probably seen those experiments where when you measure where a photon is, it turns up as a little dot like this. Doesn't that prove that a photon must be small? Well, not quite, and it's because quantum measurements are really weird. Remember that we can only talk about the energy of a photon when it has a well-defined wavelength. On the other hand, most light doesn't have a well-defined wavelength. In fact, it's a mixture of many different colors. For example, purple RGB light is actually just made out of red light plus blue light. When you add different lights together, you get weird-looking waves. Here you can still talk about photons, but you'd need to say that there are this many blue photons and this many red photons. This kind of wave is a real type of wave and they're very useful. It's called a Gaussian wave packet, and it's not made out of a single color of light. Instead, it's made out of one main color, like this one, and then a bunch of other colors that are nearby to the main color. So for example, this one that's slightly longer. When you add enough of these different colors of light together, you get something that looks like the Gaussian wave packet. And that's why this is not a single photon. This is a mix of different colors, which means it's a mix of different photons. A single photon state must be a pure color state like this one. You can see that this type of light needs to be spread out infinitely long all across the universe, which is why this kind of light, photons, they're a fiction. They don't really exist. But sometimes we can kind of approximate a photon by having a single laser, let's say, of light that's across a very big space, like, in the double slit experiment. So it's approximately an N photon state, or a plane wave, as we like to call them, but you never actually have real photons in real life. Okay, but now for the really interesting question. Why is it that when you measure a photon, it goes from being this infinitely big thing to just a single dot in a random spot? This is something it took me a really long time to get my head around, but it was thinking about the photoelectric effect experiment that finally made me feel like I understood the answer to this question. So let's go back to the experiment, or rather my cartoon version of the experiment. So one very typical way to measure a single photon of light is to use something called a single photon avalanche detector, and it's actually based on the photoelectric effect. So imagine this is our calcium metal from earlier, and we're going to shine some light on it in this whole area, right? And let's say that there's only one photon worth of light coming out of here every second. So what's going to happen? Well, what might happen is that a single electron from this calcium gets ejected. And if we're super, super clever about it, it is possible to amplify up this tiny, tiny little current to an amount that's actually measurable. And so you can measure that this electron got ejected from this calcium. But now you've learned something else as well. This photon of light that was spread all across this entire area has now been measured just inside of this confine of this calcium. In other words, you've done an approximate position measurement of this photon and you found that it was inside of here and not out here somewhere. If you make the metal even smaller and you measure an electron being ejected, now you've done an even more precise position measurement of the photon. Now suppose you made an entire grid of these little metals and you make that grid big enough to cover the entire area that this one photon will shine on. What's going to happen? Well, the photon is going to turn up in just one of those spots, randomly. This is how you get photos of single photons. It's actually a pixel array of these little photoelectric effect experiments going on. And when the photon hits one of these, then the current is detected in that pixel and that pixel's colored in. But this is weird, right? If the photon shines on the entire grid, then why don't we get a sort of mini current in every single one of these rather than a big current in just one of them? That's exactly what would happen if the electrons acted in a classical way and they were able to accept any amount of energy. But remember, the electrons don't act that way. In fact, these electrons will only accept enough energy to let them escape from the metal. Otherwise, they won't take any energy. And when you shine this light at the grid, each one of the grid points is not getting enough energy to release the electron. But the way that quantum mechanics deals with this is it says that instead of all of these pixels getting a small amount of energy, one of them randomly will get the entire photon worth. And that's where the electron will be ejected, and that's where you'll measure a current. It is unsettling that the result of this measurement is random. Like if you did this experiment again, maybe the photon will turn up here this time, and maybe next time it will turn up here.
This does explain why the electrons only take one photon worth of energy at a time though. Say there are many photons worth of energy shone on this area in a short period of time. Because it's random where those photons will show up and be absorbed, as well as when those absorptions will happen, it's very unlikely that a single electron will absorb 2 photons before it escapes.
This also explains something that I was very confused about even after I finished shooting this video. I thought that the amplitudes of these waves had to be discrete, but that's actually wrong. They can be any value at all. And the reason is because the amplitude is related to the power, in other words, the energy per second. This makes sense because if you had a light on for a longer amount of time, then you'd be using more energy than if you had it on for a short amount of time. But let's say you measure how long it takes for a photon worth of energy to be absorbed from a bit of light. If you have a big wave with high power, then it'll be a short time before the first photon of energy arrives. On the other hand, if you have a small wave with low power, then that means it'll take longer before you absorb the first photon worth of energy. But you can see how any amplitude is then allowed, because a smaller amplitude just means that you have to wait longer for the photon to arrive. But the thing that's discrete is just the amount of energy in each of those photons, and not the power itself. But a consequence of that is that it's wrong to call a wave like this a photon. Even if we make the amplitude really, really small, that just increases the time it takes for a photon to arrive. But if you keep that light on forever, which you have to for a plane wave, then photons will keep arriving very slowly forever. And so the only way to get a true one photon state is to decrease the amplitude to almost zero, but not actually zero, so that it takes an infinite amount of time before a photon of light will arrive. That's obviously fictional, but it's a very convenient fiction when you're working in theory. In practice though, when people say that they've done an experiment with one photon at a time, like for example with the double slit experiment, what they actually mean is that there was only one photon worth of energy per a short unit of time. And I feel like the results of those single photon at a time experiments are only really surprising if you believe that photons look like this. But photon states are actually just waves that spread out and go through both slits, and so of course there's still an interference pattern. Huygens Optics does a really great video where he does one of these experiments and explains exactly what's going on, so I highly recommend that. But let's go back to the main video now, because there's one last thing that I found really surprising that I want to tell you about photons. Originally, if the photon was spread out like this and had a single color of light, but when you measure it, it ends up becoming confined and could end up in a state more like this Gaussian wave packet. Doesn't that mean that it's changed color? Like, remember we said that the Gaussian wave packet mainly was this color, but has other colors in it. And so if you did a position measurement of light and at the same time an energy measurement, so you can do an approximate energy measurement, which will tell you the approximate color, then doesn't that mean that you'll sometimes measure a single color of light to suddenly have different colors inside of it? Well, I thought that was just too weird to be true, and so that had made me a bit doubtful about this entire picture. But then recently I heard about an experiment that a group had done that very cleverly confines a laser light to a very, very small amount of space. And this is the result they found. They found that there is a probability of getting different colors of light. Honestly, quantum mechanics is so weird, and I feel like I'm still learning so much about it.
I started on this video series having almost no idea what light was, even though I'd taken plenty of classes on it. And doing these experiments pretty much changed my mind on the little I thought I did know, like that light is fundamentally a particle. It took a while, and there's still lots that I don't know, but this is my understanding of light now. Light is a wave of the electromagnetic field, but what's particle-like about it is that it only delivers discrete packets of energy when it interacts with matter. If you'd like to see the full journey I took to get to this conclusion, here's a link to the series. Thank you Screen Australia and YouTube for supporting these videos. It's been so much fun.
The worst case scenario is that you end up creating enough debris that it's not cost effective to depend on space. Now, that may take a long time, but because it's a non-reversible process, once you've reached a certain threshold where you're generating debris from these collisions faster than it can be cleaned out, so it could just continually get worse unless you do something drastic.
If we continue operating the way we do today, we will have a disaster in 50 years and 100 years. It compares quite nicely to the CO2 issue and the climate on ground. So it's not our generation suffering from all the CO2 release into the atmosphere, it is future generations. But it is our generation that has to take the action. And the space debris problem is quite similar.
My name's Don Kessler. I worked for NASA until 1996 as the senior researcher for orbital debris. I started the program back in 1979, and the program is still very active today. In the 1960s, my main job was to define the interplanetary meteoroid environment.
At the time, the only space debris NASA had to be concerned about were meteoroids, many of which are generated from collisions in the asteroid belt. These asteroid collisions are a cascading phenomenon, meaning every collision creates more ammunition for future collisions. It's a positive feedback loop. Don was studying this phenomenon when he started to consider an interesting question.
When will this same phenomena start happening in Earth orbit? When will the same kind of cascading occur with satellites? And it was just a matter of curiosity as to what that number may be. And actually, when I did the calculations, I was really shocked at the answer, that it would happen so soon.
Don published a paper in 1978 proposing this scenario, predicting that we'd start to see satellite collisions in Earth orbit by the year 2000. Just like in the asteroid belt, these satellite collisions would trigger a domino effect, creating a whole bunch of debris which causes more collisions, creating more debris, and so on. His main point, once the process starts, it'll be nearly impossible to stop. This self-perpetuating phenomenon, this domino effect, became known as Kessler syndrome. The first accidental collision occurred in 1996, when a French satellite was struck by a piece of a rocket thruster that had exploded 10 years earlier, severing its stabilization boom, and for the first time, demonstrating how entangled the orbital environment has become.
In 2009, a collision happened that was by far more dramatic.
The event he's referring to was the first collision between two intact satellites, the Russian satellite Cosmos and an American Iridium.
And that was the first catastrophic accidental collision that got everybody's attention, because not only do they realize how much debris is generated when something like that occurs, but that we are now entering this phase of what we're calling the Kessler syndrome.
Just 2 years earlier, the Chinese military conducted a controversial anti-satellite test, intercepting one of their own defunct weather satellites with a kinetic kill vehicle, a non-explosive missile which relies on sheer speed of impact to destroy its target. It blew the satellite to smithereens and created just a huge mess. It was really bad.
And unfortunately, it was something that they should have known not to do.
Yeah, that's because the US did the same thing back in 1985, the first anti-satellite test, with more or less the same results.
We at NASA tried to delay that or stop that, or because they said it's going to create enough debris that we'll have to add more shielding on the space station, which was planned to be launched a few years later. And nobody believed it would make that much debris, but it did.
All of these collisions, accidental or otherwise, make a big mess of junk zipping around the Earth called space debris. It accounts for 95% of the objects in low Earth orbit and comes in all shapes and sizes. It's technically defined as any non-functional object in orbit, so there's big stuff like rocket thrusters and defunct satellites, but the vast majority are little bits and pieces called fragmentation debris. Many of these fragments come from explosions caused by residual fuel and other explosive energy sources self-igniting under the extreme conditions of space. These explosions happen more often than you might think, and as catastrophic and messy as these explosions are, collisions are even worse due to the incredible amount of kinetic energy involved. At the velocities objects travel in low Earth orbit, speeds known as hypervelocity, even an object as tiny as a screw can deliver an incapacitating strike to a satellite. In fact, NASA has repeatedly had to replace shuttle windows due to hypervelocity impacts by flecks of paint.
These are velocities we have no example nor anything that compares to that on ground. So the energy involved in these collisions is extremely high. A 1 centimeter object that size, like a cherry, hitting a satellite with 10 kilometers per second, the energy released by this corresponds roughly to an exploding grenade. You can imagine what the satellite looks like after that.
Yes, let me show you something. This is something that was shot in the lab. It's a projectile about the size of a BB, and it makes a crater into, this is solid aluminum, and this was only going about 5 kilometers per second, about half the speed of what you would expect in space.
Most of this is happening in low Earth orbit. That's the 2,000 kilometer strip of space just above our heads, where we've packed the vast majority of our satellites, including the International Space Station and the Hubble Space Telescope. The most crowded section is actually between 500 and 1,000 kilometers up. It's the densest region. It's the Highway 401 of space.
And that's what's creating the problem, because we've crowded so much stuff in that small region. And the probability of collision goes as the square of the spatial density. So you double the number of satellites, you get 4 times as many collisions. Now the space station usually flies at around 300 kilometers, but the debris that's generated at that higher altitude is being thrown down and drifting down to the lower altitudes.
But if you look at the space station surface, it is you will find craters everywhere, impact craters caused by debris everywhere. Whenever you bring some hardware down and inspect it on ground, you find craters of all sizes. What do we do with this? How do you protect the life of the astronauts? The only thing you can do is shielding.
And to protect against a hypervelocity impact, you need a special type of lightweight shielding called Whipple shielding.
Let me show you something else. The same particle that caused this kind of damage only caused this kind of damage on a surface with a very minor amount of shielding on it. And it's just almost a liquid splattered onto that.
Most spacecraft utilize this type of shielding, which can withstand impacts from objects up to about 1 centimeter. Objects larger than a softball are cataloged and tracked by the US Space Surveillance Network. Tracking is imprecise, but allows spacecraft to dodge some of the debris that comes too close. This only works for objects larger than 10 centimeters or so. Anything smaller can't be reliably tracked. For that reason, the most concerning objects are those between 1 and 10 centimeters, too large for shielding to withstand, and too small to be tracked. These objects could incapacitate any spacecraft in their path, or worse, and with every future explosion and collision, there will be more and more of these invisible projectiles going around. The problem gets worse when you consider how long objects can remain in orbit. Depending on altitude, debris in low Earth orbit may remain there for years, decades, or even centuries before their orbit naturally decays enough to re-enter the Earth's atmosphere. For example, look no further than Envisat, a defunct 8-ton satellite operated by the European Space Agency until it lost contact in 2012, becoming a massive piece of space junk in the densest region of Earth orbit. Envisat will remain in orbit for 200 years, if not removed. Experts hope to avoid an encore of Envisat and to mitigate Kessler syndrome through the international adoption of 2 clean space policies. The first will prevent explosions by requiring so-called passivation of onboard energy sources.
Meaning, residual fuel must be either depleted, burned, released through a valve, whatever. That's number one. No more explosions.
And the other is what we call a 25-year rule. Once you put something in orbit, after you finish using it, you have 25 years to get it out.
Either by moving up to a designated graveyard orbit, where it will pose minimal risk to active spacecraft, or more ideally, lowering its altitude so it will burn up in the atmosphere sooner. These policies are not difficult to follow and are beginning to be adopted internationally.
When we do these two things, that would already make spaceflight pretty safe for the future. It would mean if we do it systematically, the risk in the future would be almost the same as it is today. The mitigation measures, they help to dampen the effect of the Kessler syndrome. We are not talking about stopping it. We're talking about containing it on an acceptable level, the growth. But it will grow, even if we implement these two measures strictly. And if you want to even prevent this growth, then we need to do active removal.
We've already concluded that it's going to take something like removing 500 intact objects over the next 100 years in order to stabilize the low Earth orbit environment again.
That works out to 5 objects per year for the next century, which at least seems achievable, right? The challenge, though, is that there's no easy way to remove space debris.
We need to approach the objects that are not under control anymore, attach to them, dock with them, rendezvous them, capture them somehow, and then get rid of them in a controlled way. You can imagine this is not so easy.
Experts are working on ways to remove debris, and there are several promising ideas in early development. There are reusable concepts like tethers and space tugs, which can grab multiple objects per launch. It saves money. There are ground or space-based lasers, which can deorbit objects by kind of shooting them down, but these face political challenges. There are actually active satellites in space right now. The University of Surrey is controlling a spacecraft called Remove Debris, which will use a harpoon to grab onto debris. That's promising. And there's another single-use option like ESA's eDeorbit, currently planned to retrieve and deorbit Envisat in 2023. Just many of these ideas aren't scalable, though. That's the problem. They're expensive and complicated, and missions like these are almost completely unprecedented. The pressure is on, though, because Kessler syndrome isn't waiting, and the consequences for space infrastructure are dire.
Today, only half of the satellites actually disappear from space within the 25 years that are recommended. We still have 5 explosions every year. If we continue and not improve the way we do spaceflight, then in a few decades, some regions of space might not be usable anymore for spaceflight, or it might be much too risky to go there. And that might mean that we either lose services from space that we rely on today, or they get more expensive.
So do you think something like Kessler syndrome is inevitable? Are you optimistic that this can be managed properly, or do you think this is sort of an inevitable issue for a spacefaring society?
I think it can be managed. It can be managed. And I do believe it's time for young people to take charge, and there's a lot of work to be done. And there's enough people involved today that I'm confident that it's going to be done.
Much like other environmental and generational problems, Kessler syndrome is invisible to us. When you look up at the night sky, you don't see collisions and explosions and fragments of debris. If you're lucky and the conditions are right, you might see one white speck drifting across the sky, a tiny testament to humankind's highest collective ambitions. But that speck is at risk, along with all it represents, if we don't address this invisible problem, because Kessler syndrome isn't waiting.
Watching a Saturn V launch is still an awe-inspiring sight, but there's far more going on than meets the eye. The Saturn V was far too complicated to fly by hand, but contrary to popular belief, it wasn't the Apollo Guidance Computer or AGC in the command module doing the job. It was a completely different computer, and one which would probably have a bigger impact on modern computers than the AGC. So what was flying the Saturn V rocket? Now, as we know, the computers used in the Apollo missions were just a fraction of the power of modern smartphones, and to many they just can't believe that you could get to the moon and back with so little computing power. But they did. In fact, you don't need a massive computer to fly a rocket. In fact, you don't need a computer at all. Well, not in the way that we think. The V2, the ancestor to the Saturn V, used gyroscopes linked to graphite vanes that sat in the rocket's exhaust to steer it, and accelerometers that cut the power when it reached a predetermined height. As the distance and heading to the target was already known, the rest is pretty much physics following a trajectory curve, the same as firing an artillery shell. But of course the Saturn V was in a completely different league and much more complicated. So whilst it's doing a similar thing of going from its place of launch to a predetermined point above the Earth at a certain speed, there's a lot of extra details, and ultimately the lives of the astronauts were also at stake. It's not just the flying of the rocket that had to be done, but also things like monitoring of all the systems, telemetry between the rocket and the ground, and the emergency detection system, to name a few. This was all housed in a special section called the Instrument Unit, or the IU. This was a ring-shaped section located between the third stage and the section that held the command module and the lunar lander. This ring measured 91 centimeters high and 6.6 meters in diameter. In here was the Launch Vehicle Digital Computer, or the LVDC, then the Analog Flight Control Computer that would take the signals from the LVDC and control the engines and flight controls, a stable gyroscopic platform, accelerometers, radar, telemetry, and 4 silver zinc batteries to power the electrical systems. When the Saturn V launched, it would switch control from the ground computer to the LVDC to run a pre-programmed routine that would put it in the correct position to roll the rocket to point it in the desired direction. Once in orbit, ground stations would track its position and speed so that the correct coordinates and engine burn duration time could be transmitted from mission control to the LVDC for the translunar injection. The LVDC also controlled and kept the third stage steady whilst the command module performed the transposition and docking procedure of the lunar module once the vehicle was on course for the moon. During the launch, over 200 parameters were transmitted back to monitor vital systems as well as communications with the crew. The rocket's attitude and speed were also monitored so that any slight deviations in the flight path could be detected and corrections sent back to the LVDC. Now, when we see the Saturn V, it looks like one large sturdy structure, but in reality the Saturn is really a collection of fuel tanks held in 3 stages stacked on top of each other with powerful rockets at the base of each, all held together by an external framework which also had to be as light as possible. The combined total of these tanks held thousands of tons of liquid fuel and oxidizer, all subject to the forces of gravity and acceleration. They'd also changed their mass considerably from their launch to the separation just a few minutes later. This made the vehicle aerodynamically unstable as the fuel was used up and the centre of pressure and mass changed during the flight. The body of the Saturn was also like a flexible tube that would bend at frequencies from about 0.3 to 4 Hz as it reacted to the sloshing of the fuels and the thrust from the engines. The flight control system had to take this into account when adjusting and gimballing the engines so that positive feedback loops didn't build up, which could lead to the bending oscillations becoming so strong that they could damage the framework and ultimately break up the rocket. To help avoid this happening, the LVDC ran a major computational loop for vehicles' guidance once every 2 seconds and a minor computational loop 25 times a second to control its attitude. These timings were chosen so that they wouldn't coincide with the slosh and bending mode resonant frequencies. To highlight why this was so important, you only have to see another structural but unrelated issue that occurred called the pogo effect and resonant vibrations in the fuel piping. This is something which was well known about in rocket design and was particularly bad on the unmanned test flight of Apollo 6. The phenomenon is called pogoing because the whole rocket starts to vibrate longitudinally or up and down the length of its body, like a pogo stick. On the Apollo 6, the vibrations caused some damage to the lunar lander docking structure, even though one wasn't on board, and were so strong that it very nearly aborted the mission. A J2 engine on the second stage also failed due to a ruptured fuel pipe caused by resonant vibrations, and the wrong engine was shut down because of a mix-up in the electrical wiring. The pogo effect occurs if there are sudden changes in acceleration due to variations in the engine's thrust. The fuel, acting under the effect of gravity, can move up or down, either decreasing or increasing the pressure in the fuel lines and thus affecting the thrust of the engines. This can become caught in a cycle of slowing and surging acceleration, which flexes the entire rocket body. If the frequency of this surging matches the resonant frequency of the rocket, a positive feedback loop can occur and the amplitude of the vibrations increases so dramatically that they can severely damage or even destroy the rocket. The main cause of it in the Apollo 6 incident was tracked down to the flexing of the X-shaped crossmember which held the F1 engines, as well as the fuel pipes resonating and causing fuel pressure variations which started the whole process. Because the power of the computers was nothing like we have, things that would be done in software now had to be performed by discrete electronic circuits like resistor capacitor networks and delay lines when processing the signals that were received from the gyroscopes, accelerometers and other sensors before their values were processed by the computer. Again, this was done to remove the buildup of resonant frequencies between the rocket structure and the computer's processing loops. The LVDC computer itself was also a major step forward and operated in an entirely different way to the Apollo guidance computer, which was built by MIT. The LVDC was built by IBM and not dissimilar to one of their commercial computers, but with many architectural changes. Whereas the AGC was designed to be crash-proof by rebooting back to the same state it was just before the crash, the LVDC had built-in triple redundancy. Basically, every computation was done on 3 identical logic systems, split into 7 consecutive pipelines. The 3 results from each stage would be compared against each other by a voting system. If all 3 were the same, then the result would be passed on to the next part of the pipeline. However, if there was an error and one of the 3 results were not the same as the others, then that one would be ignored by the voting system and the results from the other 2 agreeing logic units would be used instead. By using this method, the likelihood of an error in the calculations due to hardware was greatly reduced. In fact, 1/3 of a computer could fail and it would still operate correctly. Something else that the LVDC did was to compare the current results of a calculation to the last known good value, or what IBM called the zero and reasonableness test. If the result of a sensor or a critical calculation suddenly went to 0, or it jumped to a much larger value than the previous one in the computational loop, it would ignore this new data and use the last known good value instead. This was done so that false data from a faulty sensor, for example, or a computational error wouldn't be applied to the flight controls, as a sudden large change could cause the rockets to become unstable. The stated reliability of the calculations done by the LVDC was 99.6% for a 250-hour mission, or 99.9966% for a 6-hour mission. Something which helped this was the way it was built. It used newly developed integrated circuit or logic units, as they were called. These contained a transistor or 2 diodes and a resistor, and were surface mounted onto through-hole plated multi-layer printed circuit boards. In fact, the boards from 1966 look remarkably like modern PCBs with surface mount components and 12 layers in the PCB, something that wouldn't become commonplace in modern computers for decades and shows just how far ahead this system really was. One thing that was common between the LVDC and the AGC was the memory. They still used magnetic cores, the LVDC having 32 kilobytes of RAM and a clock speed of 2 megahertz, giving it a speed of 12,190 instructions per second. A modern PC, by comparison, is about 1,000,000 times faster. A total of 40,000 silicon semiconductors and resistors were contained in the simple ICs, which made up the main processor. The PCBs that made up the LVDC were mounted into a magnesium frame, and the chassis had liquid-cooled walls to help dissipate the 138 watts that the computer used. Should there have been a problem with the first stage in some way, there was the Emergency Detection System, or the EDS. This could do one of two things. If it detected an imminent breakup of a craft, it would trigger the automatic abort sequence. If it was less serious, it would notify the crew for them to take the appropriate action. But once the abort sequence was triggered, it was irrevocable and would run to completion. The last procedure that the LVDC performed was once the vehicle had reached the moon. This was to keep the undocked third stage and the instrument unit away from the command module. On Apollos 13, 14, 15, 16 and 17, they were also directed to crash onto the surface of the moon, not only to keep them from colliding with the command module as it orbited the moon, but also to act as a seismic event that would be monitored by seismometers that had been left by previous missions. So, whilst the LVDC was the unglamorous counterpart to the Apollo guidance computer, its job was probably even more essential.
Hello, it's Scott Manley here. Lots of space fans know about the Apollo guidance computer. I myself have talked about this historic device, its famous errors during Apollo 11. I've disassembled the code and even had the chance to look inside a real one. But fewer of you know that there were actually 4 different computers on every Apollo mission to the moon, all with different roles and designs. The 4 computers were the Launch Vehicle Digital Computer on the Saturn V, which handled the launch of the monster rocket. There was the Apollo guidance computer in the command module that handled the deep space navigation needs, and there was a second Apollo guidance computer in the lunar module, which would handle landing on the moon, the return to orbit and rendezvous with the command module. Then there was the abort system in the lunar module, which was a backup system that would handle a return to lunar orbit if primary guidance failed. So there were 3 distinct designs developed and built by 3 different teams and 3.5 sets of software, since the AGC code for command module and lunar module actually shared a lot in common. And you know, being a bit of a computer nerd, I want to talk to you about how all these were unique technological creations in their own way. So let's start with the Launch Vehicle Digital Computer. That was developed by IBM to control the Saturn 1B and the Saturn V. It was part of the instrument unit fitted to the final S4B stage. This unit also included the power, cooling, communications and sensors required for the entire guidance system. The digital computer itself weighed about 36 kilograms and fit into a box about 75 centimeters by 32 by 27. The logic hardware was built out of individual transistors and diodes. These came in tiny 0.5mm chips, which would be soldered onto 1 centimeter square alumina chips, and these in turn would then be soldered onto an 8 by 6 centimeter PCB. This kind of packaging was something that IBM had developed experience with for their more earthbound mainframe computers. The computer used magnetic core memory, which came in 4096 word modules, and there would be up to 8 of these modules that could be fitted to store the program and the working memory, providing a total or theoretical total of 32,768 words of storage. There wasn't any read-only memory. The program was loaded into memory and could be modified during vehicle assembly. The computer clock cycle operated at 2048 kHz, but the processor would take about 168 cycles to execute most instructions because it's operating 1 bit at a time. So it'll run about 12,000 instructions per second. But it also had triply redundant hardware, so each operation was also performed by 3 separate units, and the most popular answer was chosen to guard against failures. There were 2 arithmetic units. One would perform your basic addition, subtraction, logical operators in a single cycle, while the other would handle the more complicated multiplication in 4 cycles or division in 8. But the 2 units operated independently, so one instruction might start a division and then spend the next 8 cycles doing something else before coming back and retrieving the result. The computer operated on 28-bit words, but each word was split into 2 14-bit syllables, and one of those bits on each syllable was a parity bit for error checking. Now, an instruction could be encoded with a 4-bit opcode and a 9-bit operand, so you'd put 2 instructions in each word of memory. Numerical data would instead be stored in 26 bits across both syllables as 2's complement integers. The computer had 2 memory modes which could be used by programs. It could be used in simplex or duplex mode, with duplex mode essentially providing redundancy by performing each read and write operation onto 2 memory banks. Since the instructions only had 9-bit operands for addressing, that meant you could only address 512 words of memory. To cover the entire memory range, the hardware had to use a complicated bank switching system, which made it hard to pass lots of data between programs running on different memory modules. In particular, this meant that some code had to be replicated on each memory module for performance reasons. Well, at least that's what the team at MIT told NASA, because early on in the development, IBM argued that the Apollo guidance computer shouldn't even be built and they should use their LVDC instead. And they produced substantial reports which the MIT team responded to with a detailed report of their own. And as far as we know, this is the only document which includes examples of how you wrote code for the launch vehicle digital computer. IBM have never really released any documentation, and there's not really any dumps of the code that ran on the LVDC. But, you know, hypothetically, you might be able to retrieve it from the memory of the LVDC in the National Air and Space Museum if they'd let a hacker near it. Finally, that digital computer is assisted by a second analog computer. The flight control computer was an essential part because it would take the commands from the digital computer and it would translate those into the engine control commands, the gimbaling. This was needed because the digital computer was too slow to deal with the real-time operation of the rocket and had to have the analog computer perform the fine adjustments to the engines to keep it straight. So the computer would tell it which way to point and the flight computer would make sure that it stayed pointing in that direction. So let's go on to the AGC. There were 2 of these in the Apollo spacecraft and they're the highest profile of the devices, the computers that were up there. When people say the Apollo computers, this is what they typically mean. Unlike the LVDC, we have complete working code. We even have working hardware thanks to some amazing hardware hackers. The AGC is so well documented that there are emulators you can play with on simulators which use the real code. And actually you can use it inside Kerbal Space Program if you really want to. The AGC was developed by Draper and they used integrated circuits for compactness. The Block 2 computer, which was used on the crewed flights, had its core logic implemented in 2,800 integrated circuits. Each of these had a pair of 3-input NOR gates implemented in transistor logic. The clock speed was again 2048 kilohertz, but the memory cycle time was only 11.7 microseconds and the instructions took between 1 and 6 cycles to complete. So overall, the AGC was significantly faster than the LVDC. The memory used 16-bit words, but one of those bits was reserved for parity. With 1 instruction per word, numerical values were reserved a single sign bit, but were 1's complemented. Unlike most computers these days which use 2's complement. Instructions were originally supposed to take 1 word of memory, but as the computer got more and more complicated, they ended up adding instructions that took 2 words of memory. The memory itself was split between 2048 words of erasable core memory, that's RAM, and 36,864 words of rope memory, which had to be hardwired in a factory and couldn't be changed at that point. The AGC also still needed to use memory bank switching to address all the memory, and this was more complicated in some ways than the LVDC, but actually ultimately it worked out to be faster and more efficient than the LVDC's implementation. Unlike the LVDC, there wasn't any redundancy. The AGC had a single core, and its approach to reliability was to make rollback and recovery from any error very fast. And this was seen in Apollo 11. When those alarms are going off, the computer is resetting and restarting and picking up where it left off almost instantly. The astronauts would interface to the computer with the DSKY interface, and this of course had the famous verb commands and the big displays. When a lot of people point at the computer, that's what they see, but the actual computer was typically, if it was elsewhere in the spacecraft, I think on the lunar module it was on the wall behind them in a sealed box that was 60 centimeter by 31 by 15 centimeters. And the whole thing massed about 32 kilograms. Now, the main difference between the command module AGC and the lunar module AGC was the code on those rope memory modules. For the crewed Apollo missions, the command module code was called Colossus, and the lunar module code was called Luminary. But there were a bunch of other versions named. Notably, the first code flown on an Apollo spacecraft was called Corona. Later versions for Colossus were known as Artemis, and the final versions of the AGC software on Skylab were known as Skylark. So the AGCs don't have redundancy. They have this rapid restart and resume capability, but just in case something disastrous happened, the lunar module carried a second computer to handle emergency situations. The abort guidance system was originally called the backup guidance system, or BUGS. But this was seen as asking for trouble amongst a superstitious bunch of engineers, so it became AGS. It was developed and built by TRW, and they again came up with their own architecture. Most of the logic was built out of a library of 8 types of integrated circuits using diode transistor logic. It used 18-bit words with no parity bit. Instructions were 5 instruction bits and an index bit and 12 address bits, allowing it to access a flat 4 kilowords of memory. The memory was all ferrite core with half of it considered erasable and half of it read-only, but this was really only, it was still using core memory, it was just the ability to overwrite the memory was inhibited. Many of the instructions took about 10 microseconds to operate, so it was about the same speed as the AGC. And divide could take as much as 70 microseconds. And interestingly, of the 27 instructions that were implemented, there were 4 that were specified that intentionally omitted the memory refresh, and that would leave the memory as zeros, but it would save power. And programmers were told to use this to reduce the power load on the system. Astronauts would interface with the abort guidance system using the DIDA, the Data Entry Display Adapter, which was a cruder version of the DSKY. In essence, you could use it to display contents of memory in specific locations or to set values. With only 4K of data to work with, it was missing many of the features that the Apollo guidance computer had, but it had enough smarts to put the lunar module in a safe orbit and then rendezvous back with the command module. The AGS was never needed for a full lunar module abort, but it did find use a couple of times during the missions. On Apollo 13, it was used to keep the vehicle stable during the short burns used to trim the entry angle. The AGS used a lot less power than the AGC, so it was the better option. And on Apollo 11, during the final rendezvous and docking maneuver, Neil performed a rotation which pushed the inertial platform on the primary guidance system into gimbal lock. Now, the AGS had its own simpler strap-down like gyro system, and it didn't suffer from gimbal lock. So that was used to keep the lunar module controllable during the final docking. And in case you're wondering, the strap-down system was easier, smaller, more compact, but it drifted more over time. So the primary guidance system with its fancy gimbals was better for long period stability. The truth is, the abort guidance system didn't get used very much because the Apollo guidance computer was so reliable. Even without redundancy in the processor or the memory, it never had any serious in-flight failures due to hardware. And it doesn't help that the Apollo 13 movie writes the AGS out of the script entirely. But as a hardcore computer nerd, I find all these different approaches and implementations fascinating. Back then, these designers couldn't even agree on how many bits should be in a word. And yet they all worked together to put people on the surface of the moon and bring them home. I'm Scott Manley. Fly safe.